So Sumit, today's session is coordinated by you.
Yes, sir.
Okay. So let us wait for a few more time
Yes,
for
sir.
others to join.
Okay, sir.
Hmm. So Sumit, please let me know when I should start.
Okay, sir.
Yes, thank you.
Good morning, sir. With your permission, can we start, sir?
Yes, definitely.
Okay.
So should I share my screen?
Yes, sir. Okay.
Okay. So I believe the screen is visible to all of you.
Yes, sir, it's visible.
Okay, so once again, good morning to all of you on day 4 of this ATAL faculty development program. So we really enjoyed to have the presence of each one of you in our program on the past 3 days. Uh, Only yesterday we had little bit of issue with the internet from Kharagpur end, rather IIT Kharagpur end. We tried to improve on the same, however, due to some restrictions, probably it was not possible. So if we just remove that little bit hiccups that happened due to internet, which is beyond our reach and capabilities to resolve, I think all of you are having, a wonderful sessions, and we hope that um, the kind of pedagogy and as well as the research environment which we try to create via this virtual platform to reach each one of you to make our topics and talk as well as tutorial and practical sessions uh, in such a way so that even if you do not belong to this particular phases of the work or the teaching that many of the expert or eminent faculty members from across the country are delivering, you do not have a lot of problems to grasp some of those knowledge. So that is the motivation, because in each and every session of ours, like, we are touching the basics, the basic portion and the fundamental topics, which are the basic necessity to understand the overview of the picture on which the topic is covered. So that you should be first understanding, like, what are the fundamental reality and the basic criteria which is required to be satisfied before we go for the advanced level phases of the particular work. So in any case, like, if you have any problem or if you have any questions also, I think all the faculty members and eminent speakers, they would be very much happy to even respond to your queries. Like, you could have their email IDs in their, personal website or maybe group website, which is available to all of you. So if you have any doubts and you need more information, you may, contact them at any point of time. Okay. So in today's session, the first sessions which we'll be covering, we'll be talking again another aspect of the work that we have been doing for the past 1 decade in our research group. This is mostly related to development of advanced level of transistor, which is actually the high electron mobility transistors. It is in short Hemp. And basically, while talking about Hemp, so it may be a completely new topics for many of you, and it may be, or the relevant portions of the talk might be known to some of you. It may be also possible, depending on the background you belong to and depending on the specialization from which you're coming from. So anyhow, so like for other theory courses as well as in other sessions, we try to touch on the basics. So in this case also, we'll be trying to see what is actually meant by high electron mobility transistors, and then we'll be seeing why these are actually necessary, and some of our work that has happened and over the last several years and we have published in the public platforms on different arenas. So some of this only will be able to present to all of you, and many things which currently we have been doing for the past couple of years, in which we have also we have recently also granted one of our Indian patents out of the work that is pursued by one of our PhD students who have recently graduated. So few of those work which are currently under the patenting process, and many things which are not published yet. So those work unfortunately will not be able to present. Otherwise, the published work and the motivation that is originated from those published work would be able to present, which are mainly to cater to the applications in the high power regime of electronic, basically power electronics applications, and also how these devices can be used for electric vehicles. So some of those aspects we'll be covering in our topic today. Okay, so in this point of view, I'll welcome you once again, and very good morning also, obviously, to all of you. Okay, so let us start today's first session, which is session number 10. Yes, and the similar thing that we wish to follow in each of our sessions, like our sincere gratitude and thanks to our mostly PhD students who have actually done work in this domain of research activities. So starting with the work of my alumni, the PhD students of our group, Rohit Singh, who is now assistant professor in Shivnadar University. And later the work is carried out by Muhammad Arif Khan, who is now a senior process engineer at AGNIT Semiconductors Private Limited. So this is a startup company which is established by IISc Bangalore. So Arif has joined initially as with the affiliations with both the IISc Bangalore as one of the postdoctoral research scientists, and then later he switched to this particular company as senior process engineer. And currently two more PhD students who are working in this domain of research activities. So one of the students is Sumit Chaudhary, who is also associated with us in the conduction or in the smooth conduction of the FDP online FDP program. And Pavan Kumar, he is another PhD student who is also working with us in these particular activities. And also our sincere thanks and acknowledgements to the research funders and international and national level collaborators that we have across the country as well as across the globe. So depending on the level of support and the funding support that we could sustain such a group and the activities that we pursue in the domain of high electron mobility transistor in our research group for the past several years. And these pentagonal structures already, all of you are now well acquainted with the different topics that we cover, oriented to different specific applications of devices that we make and systems. So till date, we have covered on topics on non-volatile memory and biochemical sensors. So today we'll be concentrating our work on Hemp devices, or in another way, we can also call it as HFET, heterostructure field effect transistors. So both names actually designate towards the same kind of devices. And in this work also, three associations or three institutions, which the name of which are already known to all of you. So Shin's University, who does the study of heterojunctions and the behavioral aspects of different heterojunction interface. That is very much crucial, as you could see whenever we are trying to cover a number of different topics also. So right now you'll be knowing that in each and every study, how crucial is to study the interface, because interface is something in which mostly the electrical performances of the devices die out. So if your interface and as well as the surface chemistry and the material science are not good enough, are not robust enough, if you do not understand those aspects, it is very difficult to realize, extremely high quality devices or systems. Even if you can assimilate theoretical investigations and can see and basically can predict that the performance would be superior enough. But however, on an experimental ground, if your interface primarily as well as the surface chemistry are not good enough for the grown materials based on which you are going to develop a system, so it is not going to sustain. So in that point of view, the level of support that we have continuously from Shin's University, our collaborator, Professor Thai, over there, it is very much of importance. And also, Hemp devices, since we cannot fabricate these in a standard laboratory in which you do not have clean room fabrications. So for that, for this particular devices, like even if you think about sensors activity or maybe memory activities on some aspects, you can do away with the requirement or necessity from the clean room fabrication steps. However, for hemp devices, we are probably much more inclined to the usage of such tools that currently we do not have, unfortunately, at our campus. So we are dependent on the usage of those facilities with our collaborators at CSIR Sri Pilani and RMIT University of Australia. And most recently also, we are trying to collaborate with other IITs in the same aspect. In some cases, we are also using INUP facilities available with IIT Bombay and IIC Bangalore. And in some cases, we are also using centrally funded and centrally available experimental tools at IIT Delhi. So those are our recent, we should say, the advancement in the level of support that we could get from other institutions. So that's why, since those outcomes have not resulted yet in the form of publications, so we just try to deviate from mentioning those institutions for the current moment. Okay. So starting with the history of hemp devices, so it is actually invented way back in 1979. Okay, so the birthplace of artificial intelligence roughly around 1959, you could see, and then various establishment of nanotechnological tools like scanning tunneling microscope and scanning probe microscope you have already seen in our introductory session on this particular faculty development program. You have seen it had happened in the year of 1980s. So now another invention, and the crucial invention, you can see it is happening around the similar kind of time, 1979. So Takashi Mimura, this is the gentleman who is actually responsible for the invention of this high electron mobility transistor. So he has been an honorary fellow from Fujitsu Laboratories Limited, and while working with Fujitsu, he tried to develop this particular devices, and his research work is actually based on another work which was that point of time been taken care of by Dingle and Stolmer at Bell Laboratories, who are working on the modulation doping of heterojunction superlattice. So these three gentlemen actually, Laughlin, Stolmer, and Sui, they have gotten also Nobel Prize in 1998, in which actually they have probably did some advancement in their studies, which they have started working on modulation doping of heterojunction, and later they have worked with quantum fluid to develop the famous phenomena called the fractional quantum Hall effect. And out of this work, they have gotten a Nobel Prize in physics way back in 1998. So their pioneering work actually motivated Takashi Mimura to develop the concept and probably develop or implement the concept which is triggered by Dingle and Stormer by modulation doping of heterojunction in the form of a device called the high electron mobility transistor. So that was the initial background of the historical development for HEMT. But obviously, since we mostly belong to an engineering point of view, or from engineering background, mostly majorly. So basically, even if we think about some kind of applications, as I have mentioned when we discussed about sensor technologies as well as for memory devices also, even if we try to concentrate on development of a new device or system, always it should be oriented towards some kind of applications, or maybe even if the applications are satisfied, by some of the devices or the systems which are available in the commercial market as well as in the research academia. And if you're trying to develop altogether a new system, so basically the new system should be having some edge with respect to the conventional systems. So now the Hemp, which was actually coined way back in 1979 and later developed by a number of different researchers working on different aspects of Hemp devices or HFED devices based on different types of materials, not only concentrating on a specific group of materials, but working on different types of materials. So the motivation was to realize a system in the domain of power electronics. Basically, to realize extremely high amount of power. As you could see the plot that has been taken from this particular web link available in the Mitsubishi website. So if you look at the spread of the power output as well as the frequency of operations that we are trying to realize for or to meet with a number of applications, as you can see, like be it the satellite communication, be it different phases of telecommunication window, be it the radar communication, be it the communication that is used at the war zone, be it for any type of space mission that a country might be having. So if you think about all those applications, so always you should be requiring extremely high amount of frequency. And not only that, if you require extremely high amount of frequency, so basically you're transferring lots of, or basically you're looking for enhancement of the data rate. Today in the age of the big data, so one could imagine that what is the amount of data which is generated for every nanosecond to every millisecond from a particular source point, and what kind of data rate is required if we need to constantly have a communication from the source point to a multiple destination point, not only reaching from the source point to destination point, also receiving the data of the same. So now you can imagine how many number of gadgets, how many number of laptops, handheld gadgets, or anything that you may be having. So what kind of data rate we are now dealing with? So it does not only require extremely high value of frequency that is required to satisfy that kind of data rate, but also in order to reach to that kind of frequency, you also need the amplifiers that is used at the destination end as well as at the source end, also in order to augment the signal to noise ratio in the communication window or maybe the channel. You should be requiring extremely robust technologies in terms of amplifiers. And in many phases you need also converters in which you can convert alternating current to direct current. Even from direct current to another level of direct current can be diminished mode of direct current, it can be higher mode of the direct current, depending on the kind of transformers also you're using at the source end, at the destination end. So not only you need a system that should be sustaining such high amount of frequency, but you should be also requiring extremely high amount of power if you're looking for number of applications that we need to satisfy. So we are talking about hundreds of watts to kilowatts amount of power, and also you're looking for applications in which you can satisfy not only 1 or 2 gigahertz applications, but you should be looking for applications in which you can go beyond even 20, 30, 40, 50 gigahertz and so on and so forth. So over the period of time, you could see initially all our transistors, even though it was initially established on germanium-based semiconductors, slowly, due to a number of advantages, people switched from germanium to silicon-based technology for several decades. And still now, people are working in silicon-based architectures. But in this particular domain of activities, like we have silicon-based in a complementary MOSFET structure, CMOS, we have also tried to toggle with the channel mobility. In sometimes we have seen applications in which the channel material is switched from silicon only semiconductor to silicon germanium based channel, in which by playing with the mechanical strain that can be originated in the channel, one can fine tune or play with the channel mobility, because high channel mobility is always required to generate such kind of high frequencies, obviously. Sometimes also silicon LDMOS, like laterally diffused MOSFETs architecture, and many other architecture was developed based on silicon based technologies only to satisfy the requirement, the high amount of power. However, it was seen for the past several decades that this kind of change in the morphological aspect, or probably coupling with another different material based on the silicon, does not satisfy the present and future requirements of frequency and power. So that's why slowly and surely many other compound semiconductor materials have come up into the arena. Compound materials such as gallium nitride, which belongs to group 3-5 of the periodic table, or maybe gallium arsenide. So people are looking for technologies based on other schemes also, like gallium oxide nowadays very much prevalent. Sometimes zinc oxide people are using, maybe silicon carbide based technologies people are using, indium phosphide based technologies. So not only people are restricting themselves on their work on silicon based technologies, but over the past several decades we have seen many other technologies based on compound semiconductors have come up, and resulting in different types of transistors, mainly the switching devices. So Hemp or HFET or heterojunction bipolar transistor, many other things have come up into the picture, in which we can satisfy, or the applications which require high amount of frequency and high amount of power are actually satisfied. So just looking at the trend in the wireless communication, so people nowadays, we talk about 5G, 4G, 6G, 7G communications window. So all these different G is actually related to the kind of generation of the communication. So 1G we started with the analog mode, 2G we started with the digital, then slowly and surely we have just worked on the international mobile telecommunication window, and then we switch to other different generations of the telecommunication window, in which we are talking about enhancement of data rate starting from 10 or roughly around 10 kilobits per second to up to hundreds of megabits per second, or even gigabytes per second, so on and so forth. So basically, if we look also at the trend in the advancement of data rates that has happened in the communication window. Again, this picture is taken from the Mitsubishi Electric website. So this also tells about the advancement that is required to cater to the requirement in communication or wireless communication in that kind of window. So number of different technologies are also developed over the courses of years for the past, from 1990s to 2020. Even people are working on different other advancement operations in the telecommunication window, in which continuously they can satisfy the big data communication, whatever we call it. So that's why the advancement, or with the advancement in the technology, all these phases like big data communication, internet of things, or internet of everything nowadays we call it, because everything is connected to everything. Okay, so whenever this connectivity is improved, and this connectivity is improved in terms of by non-reduction of the data rates also, so you could imagine what kind of data rates are actually required. And in order to satisfy those kind of data rates, then what kind of devices and amplifiers and converters will be requiring at the source, destination, and the channel end. Okay. So now looking at the fundamental aspects, like if we need to satisfy those kind of operations in terms of frequency, the requirement of extremely large amount of frequency in the order of hundreds of gigahertz, like starting with tens of gigahertz to hundreds of gigahertz maybe in future, and also to realize extremely high amount of power. So what is the fundamental aspect which is required to be satisfied if you're looking at the picture from a transistor? If you're looking at the gain that can be ascertained at the output circuitry if we concentrate on transistors. So there is one, figure of merit we call transconductance, which is nothing but uh, a ratio of your saturation drain current with respect to the variations of the gate voltages. So the mathematical formula is also given over here, which is again, you could see it is dependent on a number of different constants. So as you could see, W, L, and Cox, which are used in this particular formula, these are nothing but the transistor width, length. So basically, we're talking about the geometry of the transistor. And obviously, the oxide or the type of oxide material, or maybe the dielectric material, like oxide, we are saying because mostly some kind of oxide we use at the gate as a dielectric material whenever we are trying to make a kind of capacitance so that we can control the switching on and switching off of the channel. So prevalently we use some kind of oxide material. So even though the performance needs to be satisfied by a dielectric material, so in general we call it as COX. And then also it is satisfied, or this equation is also dependent on another two phenomena, which is the mobility of electron, because mostly we know for a number of different classes of materials, hole mobility is lower than generally the electron mobility. So the type of transistor that we make, we want the electron should be playing as the role of the majority carrier. So can I ask the participants, like, why generally we are looking for a transistors, or maybe why the hole is having lower mobility as compared to electron? Can anyone tell me? Any of the participants?
To their mass, sir.
Yes. Thank you so much. Yes, due to the effective mass, because we know one can calculate the effective mass of any carrier if you basically take the derivative from the dispersion relationship that one may have, and from the dispersion relationship that one can originate from the orientations of the valence band as well as conduction band. So from taking of the curvature, or basically finding out the extrema values of the curvature, so one can evaluate the value of the effective mass. So effective mass of electron as well as effective mass of the hole. So the effective mass of hole is always observed to be on the higher side as compared to that in case of the electron. Yes, thank you so much for the answer. That is correct. And the other thing which is actually helping to modulate the transconductance is the VTH, which is the threshold voltage of the transistor. And the second factor, and particularly this factor, GM, is actually responsible to realize extremely high amount of gain in the transistor. The second factor, since we will be talking about frequency of operations of the devices. So frequency of the operations of the devices, or rather the cutoff frequency, it is given by, which you can see, GMD by these factors. Even though all these factors at the bottom, even if there are less probability that we can control, because WL, again, these are dependent on the geometry. So due to the fabrication that we generally follow in the clean room fabrication steps, they have some kind of limitations in which one can play with the values of W and L. One can play with the value of dielectric constant epsilon, but to a less extent. By you can change the growth conditions of the gate dielectric material, you can change probably number of different materials, but again, the limitations will be there. Okay, and D is the oxide layer thickness. Again, it is dependent on the clean room fabrication steps. So again, you can see mostly the cutoff frequency would be higher if your GM value becomes larger. And the current density that we all know from the Ohm's law, it is nothing but sigma multiplied by the electric field of operations, which is again given by 3 different factors. If we split out sigma, now sigma is a product of the electron density and again the mobility. And if you are talking about the power output of the devices, it is again dealt with these two fellow, ID max, basically current and voltage. And if the maximum value gives you the maximum power output. So if your value of J becomes much larger, then obviously the value of ID that you can get would be higher also. And the value of VD is always controlled by the value of input voltage. So in order to have high amount of power, one should be looking towards satisfaction of high value of sigma, because E is controlled from the input end. And for the high amount of sigma, you should be having extremely large value of this product, Ns and mu n. So Ns is the charge carrier density and mu n is the mobility. So if you have some kind of device in which you can enhance this particular product, and that is actually the basis of generation of this concept of modulation doping of heterojunction, in which even if these people, they have realized a particular system of a heterojunction, they have worked with the geometry in which they have enhanced this product in a huge amount of way to get some particular level to realize extremely high amount of power devices, not only with the high frequency. So if we look at the energy band diagram point of view, and these are some of the established commercially available Hemp devices based on the gallium nitride systems. So this is the overall picture of gallium nitride based commercially available Hemp devices, and the picture of it, how it is actually fabricated in the clean room processing techniques, and how it is also can be mounted on different other substrates. Like here it is mounted on the diamond substrate. Similarly, one can also mount this kind of devices on silicon carbide or any other substrate which can help in the power dissipation or the heat dissipation, because these are generated to realize milliwatts or even what level of power. So one can imagine the amount of temperature the active region is going to generate. So one has to deal away with this kind of heat to the outside, so that disruption of the channel and the junction at which mostly this product of Ns and mu n are happening, they should not be destroyed. And these are roughly the schematic of these industrial Hemp devices are shown in this particular slide also. So more on this one also we'll be talking later on. So basically, if you look at the schematic, it is nothing but actually having a heterojunctions of one type of semiconductor, and on top of you have another type of semiconductor, and this semiconductor gallium nitride, which we call it as a buffer. So those should be having a larger amount of thickness, and in between this buffer and our substrate, which is in this case is silicon, there is a transition layer. So people use different types of transition layer, or also sometimes they also call the sacrificial layer or maybe interface layer. So depending on the type of work and the type of materials people use, they have different variations in the material that should be used the transition layer. But the purpose is not to generate a kind of defects in the buffer layer, because the channel which is supposed to create or help the device to work as high electron mobility transistor, that is generated at the junction of the buffer and the top burial layer, roughly around this region, if we look at the horizontal section of it. And the top, which is known as the burial layer, they should be having much lower thickness as compared to the buffer, and the band gap of the burial layer should always be larger in comparison to that we have for the buffer layer. And this is your gate structure with a particular metal interface, and as well as the source and gate terminals that is also mentioned. Okay, isolation geometry you may have, which generally removes the crosstalk from one device to another. These are roughly the schematic of any kind of Hemp structure one may have. And this is the energy band diagram. So before the junction formation, this is roughly the location of the Fermi energy level in the buffer layer. And since the barrier layer should be having larger band gap, so you can see the split between the minima of conduction energy band and the valence energy band. So this gap is much larger as compared to this gap for the buffer layer. So before junction formation, this happens to be like this. And once the junction is formed, then you could see it can form something like this one. But whether the location of the quasi-Fermi energy level that you could see at the thermodynamic equilibrium, whether it goes through this conduction energy band or not, that is dependent on your band gap engineering. Whether the positioning of, in this case, the positioning of the conduction energy band from the buffer to the barrier layer happens in this mode or in another mode, it is always dependent on the kind of design of the materials which you are going to use to make such kind of heterostructure. So this geometry now we are showing in terms of the theoretical point of view, but there are some experimental tools also in which one would be able to understand whether they will be having this kind of geometry in the energy band diagram or not. Applications already we have talked about, low noise amplifier, satellite communication, compact radar. So we do not need to go into more details, but our motivation is always to reach for high power and high frequency in applications. And that's why, based on this prevalent nature of this kind of devices, slowly and surely the materials based on which this high electron mobility transistor is based, those are mostly wide band gap semiconductor materials, in short WBG we are calling it. It can be gallium nitride, zinc oxide, gallium oxide, silicon carbide, and many others, mostly compound semiconductor devices. Those are shifting silicon slowly and surely out of the picture. If we look about their applications from various sectors of communication window, consumer electronics, automotive industries, and many other places in which we are also using renewable sources of energies. We are talking nowadays about electric vehicles. So if you think about any kind of applications in which you need extremely large amount of power that we have seen earlier also, we need these devices and we need these materials. And if we simply look over the last 6-year window in terms of the market evaluation, even if we look the amount of enthusiasm in terms of the finance that is put forth across the entire globe, and if we look at the sectors like industry, telecom infrastructure, automotive and transportation, mobile and consumer, computing and medical applications, so there is a rise of roughly 2% if we look at the window of transiting from 2018 to 2024. So across various sectors, huge amount of financial interests are there. Even if people start working, or even if to basically encourage people to demonstrate and also translate the technologies from the academia to industries. So if you look at various aspects of Niti Aayog government of India also, so initially they have a clear roadmap that by 2030 only electric vehicles are to be sold in Indian market. But however, even though this kind of very novel idea about shifting from the petroleum industry or shifting from the non-renewable sources of energy consumption to renewable sources of energy, or transiting from the carbon generated systems to non-carbon systems like electric vehicle, the novel technologies, even if it is difficult to realize completely to overturn by 2030, but slowly you're seeing the motivation is to realize towards shifting the entire transportation towards 100% electric vehicles. So this is a beautiful motivation and the thrust that has been given by Government of India to push forward and go ahead in the future in which we are transiting from our petroleum products into the electric engines. So some of those applications in which these hemp devices are also proved to be very much essential in importance in the realizations of electric vehicles, those aspects also will be seen in brief. Looking at the power versus frequency applications on power electronics, yes, we have talked about number of different technologies which were earlier, established mostly on silicon-based technologies, but nowadays, if we talk about so many different applications, yes, compound semiconductors, they are having tremendous, competition with respect to the so-called conventional silicon-based technologies. And in our group, we are working on one of the supreme, WBG material or wide bandgap material, which is zinc oxide for the past 1 decade, and which is also proved to be beneficial to realize very good and high quality, high electron mobility transistors because of number of different fundamental aspects which are satisfied by this particular material. Because if somebody would like to realize extremely high amount of power and high amount of frequency of operation, so obviously the breakdown voltage or the breakdown field that this kind of material or any new material that should be sustaining should also be extremely high. So if you look at zinc oxide, it has 3 times of larger band gap as silicon, so it sustains extremely high breakdown field. The output capacitance is much lower than the silicon single junction field effect transistors for zinc oxide devices. If we look at the reverse recovery charge, another phenomenon that limits the switching operations of the devices, because any device or any high power device you use, it does not only need to realize high amount of gain, but also realize, fast switching speed. Okay, so in order to do that, you need, the reverse recovery charge and time that should be of extremely low amount. And these values are 100 times lower as compared to conventional silicon. Extremely low amount of on resistance and compactness and weight reduction, extremely cost effective nature, because we can not only realize zinc oxide by so-called expensive growth techniques like epitaxial system, but also one can also realize by simply usage of sputtering techniques. Okay, so they have also extremely large amount of thermal conduction value. Those will be required to be satisfied if one is looking to establish, a system which can lead up to generations of huge amount of temperature. For power dissipation also you need high amount of thermal conductivity, saturation, deep velocity, electric breakdown field. So if you look at all those operations, this material is having huge amount of potential. And also we could see in our group also, we could actually realize extremely high quality, high electron mobility transistors. And this particular fellow, which we talk about, low on resistance. So low on resistance is actually determined by 3 factors. So one is the drain resistance, source resistance, these are the contact resistance that we talk about, and this is dependent on the type of metal and semiconductor contacts one may have. But it is also dependent on RSH, which is the sheet resistance. And this sheet resistance, as you could see, it is like inversely proportional to the electron charge and product of 2dg density or sheet charge density and the mobility. So if we realize a system in which we can enhance this factor by huge amount of value, then one can realize extremely low value of RSH. And if your value of RSH is extremely low, eventually you should be having extremely low amount of R-on resistance. But this fine-tuning is not possible in silicon technologies. So that's why the zinc oxide material proved to be extremely potential to realize high quality hemp devices. Okay, so talking a little, I'll be touching on little bit of details also about how one can generate, either we can call it shift charge density, or sometimes also, since it is generated at the junction of two different materials, we can also call it the two-dimensional electron gas. In short, 2D density. So generally the 2D density, it is dependent on a factor which is called the sigma net, which is nothing but the polarization shift charge difference at the barrier buffer interfaces. Okay, so the fundamental concept of it is actually coined in this particular work published in APL way back in 2010. So interested readers may also look for this one. So the value of NS is dependent on the polarization, shift charge difference of the barrier and the buffer layer, and another factor which is dependent on is the value of the kind of trench that you could have at the barrier and buffer junction, which is the conduction barrier offset or conduction band offset you may have. So you can have a theoretical estimation by which you can calculate what kind of conduction offset or band offset you may have, because mostly we're talking about motion of electrons in this case. So we are much more oriented towards knowing what is happening at the conduction band edge. So it is always dependent on to know what is the energy band gap at the barrier and the buffer. And if this value becomes much lower, then obviously the value of 2D density also becomes much lower. So what is our target then to generate high amount of 2DG is actually increase sigma net, the value of sigma net and the value of delta EC. So that becomes the energy band gap engineering and the choice of materials that we may have. So in this case also, what we did, we played with a number of different compositions of the barrier layer in which we have tried to use magnesium doped zinc oxide material, and a buffer layer we use a zinc oxide material. We have tried different combinations of this one to actually play with what value of 2D density we can enhance. Okay, so we also should be knowing from the material scientist point of view that zinc oxide generally has Utzeit crystal structure. And if you're looking to enhance the molar concentration of magnesium to the mix, it is trying to go towards the rock salt nature. So there should be an equilibrium maximal point of X value, or the magnesium doping value in the zinc oxide matrix, up to which the Utzeit crystal structure is actually retained. So those are actually dependent on the type of growth system that we use and the type of material system that we may want to have. So this becomes lots of experimentations also. So I'm not going into those kind of details. So let us concentrate only on some kind of work. So I'm just skipping this work because this work on how we have played with the geometry of barrier layer and the buffer layer. So we have published this work in IEEE TED way back in 2017 also by Arif. This is Arif's work. So interested readers can also go through this particular literature. So lots of mathematical equations are also there. So I'm not just going into the details of each and every of these equations as of now. So that the entire event of covering this lecture to give you the glimpse of the work that we are doing and how much beneficial are these actually. So I'm just skipping this slide also for the time being. Yes. So this is another important aspects which we have realized. So in this case, in the figure, that you could see that the value of the 2D density, two-dimensional electron density, we can fine-tune with the atomic compositions. The atomic compositions of the barrier layer and the atomic compositions of the buffer layer as also. Earlier we have seen the buffer layer, we are trying to use zinc oxide. Now we have added another into the mix. So we are using cadmium doping also of zinc oxide, because our motivation is what? Our motivation is to see that how high of the two-dimensional electron gas density we can reach, because that determines extremely high amount of GM and also extremely high amount of power as well as the frequency of operations. And as we have already seen, the 2D density is dependent not only on the sigma net, but it is also dependent on the conduction band offset parameters. So that's why we're trying to use material systems in which we can play with the achievement of the optimized maximum amount of delta EC value. So we have also tried using cadmium doping of zinc oxide in the buffer layer, in addition to the usage of magnesium zinc oxide. So as you could see, whenever we are trying to move from the system from MgZNO to MgZNO CdZNO, the value of 2D density becomes higher depending on a particular combination of atomic compositions. So we have a jump roughly around 10 times enhancement for this system, in which we have magnesium doping of 15 atomic percent in the barrier layer, and cadmium zinc oxide jump. You could see the Y variation on this axis. And if we fix cadmium composition and varied magnesium composition at the barrier layer, so roughly the jump is 6% or 6 times rather. And we have also seen these values that we have obtained, like both experimentally as well as we have done some analytical modeling also. So after developing an analytical model also, we have satisfied our findings with the available literature results. So we have seen that actually our theoretical prediction is correct in terms of the validation or after validation of our model with the valid experimental data that is available in the literature. So we could see, even if we want to transit from magnesium ZNO system to magnesium ZNO cadmium ZNO system, there is a huge jump of 2D density. And it is not only dependent on the chemical compositions of the barrier and buffer layer, it is also dependent on the thickness of the barrier layers as well. So here you could see we have tried to change the barrier layer thickness, or that is the magnesium zinc oxide system, from 10 nanometer, or maybe starting from 5 nanometer, we have gone up to 30 nanometer. So you could see the jump is actually initially huge, but then it saturates. It does not depend anymore, even if we want to increase the barrier layer thickness. So what we can do now, we'll just stop here, give a break of 10-15 minutes, and then we can come back to discuss few more findings in this particular aspect of work. So as of now, if you have any questions, we can happily answer those. Yes, Sumit, do you have any questions from the audience?
I think not, sir, because no one is asking. Any
Okay.
questions from audience?
Yes, anyone who would like to discuss, ask any questions, I'm okay to answer. And we can have a discussions also.
I think it's all clear for me.
Okay, fine. Then we can give a break of probably 10-15 minutes, and then we can again gather at 10:15.
Okay.
Okay, thank you.
Now I request all the participants, please switch on your videos. Participants, please switch on your videos. Again, I request you to please switch on your videos so we can take a screenshot. please switch on the videos for some more participants. If can switch on their videos, then we can take the screenshot. Okay, I think participants has gone.
Sumit, are you there?
Yes, sir.
Okay. Okay, so let me share my screen again. Are you able to see?
Yes, sir. It's visual.
Okay, thank you. So welcome back. 1 second, let me get laser pointer after the short break. Okay, so here I'm giving you a glimpse of one of our structures, which we have also fabricated recently and published this particular paper, IEEE Electron Devices Letter, way back in 2018. So 3 years before we published this, in which we have grown these systems by using dual ion beam sputtering deposition system that we have at IIT Indore. So these are the different growth parameters to grow the buffer layer as well as the barrier layer in these cases. So as you could see, and the formation of the two-dimensional electron gas that you could see at the junction of the barrier and the buffer layer is designated by this schematic of the red junctions. And this is the typical thickness of the layers, which are also mentioned in this particular case. So we have evaluated the values of the shift carrier density or 2DG density with respect to varied compositions of the barrier layer, as you could see, as the barrier layer composition is actually going high. So one could see the values of the shift carrier density whenever it is established on silicon, and the same values whenever these two junctions are mixed together. The barrier is magnesium zinc oxide and the buffer is cadmium zinc oxide. Then how actually the 2D density is varied, and we have reached up to 10 raised to 14 centimeter inverse or centimeter minus 2, so per square meter. And that is the generally the convention to use or depict the unit of the 2D density. So we could see by the enhancement of the magnesium composition, so one could imagine the value of the conduction band energy offset is also getting enhanced, and slowly we are seeing an enhancement with the 2D density. So this value is extremely high for any types of Hemp devices based which are based on this type of heterojunctions. And also, in order to segregate whether or to satisfy whether we are getting a 2DG formation or not, so it is essential that once you calculate the 2DG density, you need to find out whether these values are actually remaining the same with respect to the ambient temperature. So we measured the value of 2DG density as well as electron mobility that we can find out, and it seems to be constant even if we started the ambient temperature from liquid helium to up to room temperature. So these values are constant. It does not make any changes. So that confirms the formation of the 2DG density at the junction of the barrier and buffer interface. And another experimental evidence that we can obtain is the capacitance voltage measurement, in which slowly what we did from the top layer, we tried to estimate the value of the 2DG density, or basically the carrier density. So top layer means this is roughly the thickness of barrier layer, 30 nanometer. We know we have started with the 30 nanometer, so we could imagine when we started from the top, the 2DG density or the carrier density value was low. As soon as we reached the barrier layer or the barrier layer and buffer layer interface, we could see suddenly a jump in the carrier density. So that is also another experimental evidence that we are having clear formation of 2DG density, and this measurement is carried out at room temperature. So once we have done these two experimental evidences, we are crystal clear that we are actually having a formation of a notch in the energy band gap, or rather in the conduction band energy, and also the formation of 2DG density at the barrier and buffer junction. Okay, so yeah, we did a number of different studies also and tried to see the performance of our system with respect to many others which are reported not only by sputtering techniques but also by epitaxial techniques. and the predictions and also the experimental evidence that we have for our grown or the DIBS grown system in our lab proves to be the best amongst the others reported in the literature. Then these are the conclusions, like we have reported 2D density. So all these things we have done. So after that, what we did, as we have also mentioned last time also, like whatever systems you try to make or you actually make it for the first time in the literature, always need to compare the outcomes with the existing technologies or systems. So also we have tried to pinpoint the values of the 2D density and also try to compute the product of 2D density and electron mobility. So we could see these particular values are actually, these values are much higher in comparison to many others which are reported in the literature based on similar kind of system, based on even gallium nitride based system deposited by extremely expensive like plasma assisted molecular beam epitaxy, or maybe molecular metal organic chemical vapor depositions, or atomic layer depositions, or metal organic vapor phase epitaxy, whatever you call it. So depending on all those growth techniques, the values that we are getting for 2D density are not only extremely high, but the values which govern the functioning of GM as well as the output power is also comparable with respect to many others which are reported in the literature. So by the usage of DIBS, it does not only reduce, the fabrication costs which are to be satisfied if we try to make these systems, but the performance, if you need to compare the performance of these devices, which are also comparable to those which are actually manufactured by extremely expensive epitaxial growth techniques. So this is the typical, the clean room processing techniques that we have followed in our cases, by which we make ultimately these two types of, schematic diagram of the Hemp devices, or in this case also we are terming it as the metal oxide Hemp devices, because a minor change what we did at the gate dielectric, instead of connecting it directly with the metal, what we did at the gate, we have also tried to use an oxide layer, which is aluminum oxide that you could see. We have deposited it by ALD by using the help of our counterpart at RMIT University, Australia. So initially we started with the metal context, and then later we came to know with number of iterations and operations of this geometry that we can have, that even if we use a very small amount of or small thickness amount of dielectric layer, the performance is enhanced by a large amount of value. And the top diagram shows you like how generally from this basic heterojunction, once you deposit your positive photoresist, then you go and realize by the standard clean room techniques for the active area or active island formations on the active zone. And then again, doing the second stage of lithography to carry out the formations of the drain and source contact, which you could see on the schematic. And after that, the third stage of lithography forms the gate junctions in these cases. Okay, so this is the typical clean room device fabrication ways about fabrication of such Hemp devices. But the final product, which is of essential for us, those in this case roughly you are seeing a channel width of only 2 micron, and the distance of the separation between the drain and source contacts is roughly around 6 micron, and the width of the channel on the other directions, which is not shown over here, it is roughly around 50 micron. So we have played and still playing with lot of different dimensions of the clean room device fabrication processes, and the most valid source and drain contacts, that should be ideal an ohmic contact in these cases, so that you could reach with the combination of titanium, aluminum, nickel, and gold on both the cases, which is proven to be working as a perfect source and drain contact, because in order to reach this transistors or high quality of transistors, one has to be very much careful about the contact resistances. So if the contact resistance of your devices are very high, then this device is no longer, or device is rather not useful to be used as a transistor. So that's why the combination, like even if this picture seems to be, very much simple to fabricate, like all these, thickness values and everything which you are seeing. So these values have come after a lot of iterations and a lot of experimental and fabrication related work. Okay, so this work which you have done a couple of years ago, still the optimization stage is going on. So one could imagine, like even if the structure seems to be quite simple to us, but it is not. So it needs to go through number of different iteration processes, number of different deposition optimization processes also, and the processing optimization in different steps also, because it requires, lots of depositions of materials like semiconductors, maybe dielectrics, maybe combination of metals, and doing some wet chemistry labs also involved, like removal of materials whenever we talk about. So we need to look at what kind of chemicals are actually reacting to what particular amount of, or what particular material in those cases. So many aspects are involved, as we also discussed in our session 1 in this particular FDP program, that lots and lots of expertise, not only through the design engineer, but electrical engineering, but also material scientists, physicists, and chemists. So many people from different institutions are involved to solve out the best combination possible for this particular heterostructure to realize extremely high quality hemp and MOSFET devices. So the typical values of the gate dielectric material along with the metal combinations are also shown. The first stage you are seeing, it is used by aluminum oxide, titanium, platinum, and gold, and the second one is aluminum oxide, nickel, and gold. Okay, so these several things we have tried and trying to see which one works or performs in the best way for the devices that we can manufacture. Okay, so this is another phase, critical phase, I should say, and this work also published, last year in IEEE transaction on electron devices. So this work in which we have just submitted, in which we have just established, source and drain contact combinations. So as of now in the picture, you could see we have tried 3 different metal combinations, and by using the transmission line measurements, using different, intercontact distances, the various values of intercontact distance, like starting from 20 micron to up to 1600 micron, on based on the silicon substrate. So these contacts are generally deposited, and then one needs to calculate the current voltage characteristics from all these devices, and from the slope of it, one needs to find out what are the values of the sheet resistance of these values and the contact resistance parameters of these values. So out of which we have seen that these 3 combinations are the metal combinations that we are choosing or showing you in this particular slide. And this is actually the optical image of the or the camera image of such kind of TLM geometry that we can realize on our heterostructures. Okay, and on the next slide, we'll be seeing how the results are actually displayed, even if we try to change the metal combination, which is shown by 4 metals used together, to a 3 metal combination and 2 metal combination in this section 2 and section 3. And also, in together with the TLM measurements, what we did in this study and published in this case, that we tried to use another sacrificial layer that we talked about, or the special layer, whatever you call it, in the form of yttria on top of silicon. Like rather than growing magnesium ZNO and CdZNO directly on top of silicon substrate, we tried to first deposit yttria on top of silicon, and then tried to deposit magnesium ZNO and CdZNO. And then this HRTM results tells us that the combination, or basically the ACD images, you could see, bright, linear dot position. It actually tells you the crystalline quality is improved. If you look, for example, in figure B on this case, that these dots are scattered everywhere. So the crystal quality is getting damaged. Even if we try to realize cadmium zinc oxide and magnesium zinc oxide directly on top of silicon. But even if we use roughly a 30 nanometer, in this case, we have tried only 30 nanometer of yttria. And because this was the first time we're trying to see what happens if we try to deposit yttria on top of silicon, because that time we have already realized very good quality of memory devices in which yttria is proved to be perfectly lattice matched with silicon. So in that case, we tried to see whether it has any effect on the heterostructure also for Hemp devices, and we saw yes, it has huge impact on the Hemp devices. And here what we did, we have tried to find out the combination of the product of this 2D density and electron mobility, and we found out that this product is the largest for this particular combination, or MCO2 we are terming in this case, rather than the other two counterparts, MCO1 and M0. And in this case, what we have told you, we have just tried to also pinpoint the same thing, the findings from these two figures, in which we are trying to find out, the total resistance that we could find out dependent on the intercontact spacing for metal combination 1, 2, and 3, and contact resistivity. We have also plotted not only for this different combination, but also after contact establishment, we also hit the contacts at a high temperature. We call it annealing. So depending on the annealing treatment, we have established that the type of the value of contact resistance and the sheet resistance parameters, those are the least for the combination of metal that we use for type 1, and these values are extremely comparable to the best reported results of such relevant parameters on gallium nitride systems. And these are the typical camera images of the Hemp devices that we have manufactured in combination with our collaborators in RMIT University, Australia. So in this case, you could see 25 Hemp devices which are housed on the silicon substrate. And these are the some values of the drain voltage and drain current, basically output characteristics. And we have also performed the measurement of our devices with respect to the best reported results on the gallium nitride ever in the world. And this is the best reported results available on the zinc oxide system grown epitaxially. So from the epitaxial zinc oxide system, the performance of our system is much superior. But still, we need to work more to reach the best reported results available for the gallium nitride cases grown epitaxially. Okay, so here also we plotted the power density with respect to the drain voltage, variations, and also we have found the results of our devices are extremely good in comparison to many others reported in the literature. We have done also reliability, because even if we are trying to make this system, transferable to actually the commercial market, so reliability measurements also we have done. So we have tried to see the output characteristics on day 1 and after 3 months when the devices are manufactured, remembering that we have not kept our devices in a normal clean room environment, but a simple laboratory room we have kept our devices, and this performs really well even if after spending 3 months. We have also seen the kind of gate leakage that we may have for our devices, and we could actually see the performance of our devices based on both the type of gate dielectric system that we have seen in the previous slide, that the gate leakage management is extremely robust in comparison to the other similar type of devices which are established on gallium nitride. Okay, so for electric vehicle, if we now spare our thoughts about how this will be applicable for electric vehicles and maybe for the energy storage applications. So these are typical block diagram of electric vehicle as you could see. Okay, and in these cases, the boxes which are marked as DC-DC converters, so these are of very much crucial to control various sectors of an engine or electric vehicle engine. Be it a motor control unit, be it a charger unit, be it an auxiliary power supply that is required to satisfy number of different power electronic tools or gadgets which are there in a car. Okay, so looking at different levels of supply, why DC-DC converter is used? Because always you're just trying to satisfy the power requirement. If you're looking for a power requirement that is required to charge a laptop or maybe a mobile inside a car, that requires a particular amount of voltage that you may be requiring. If you're looking to charge your car battery, then you would be requiring another level of power supply, so on and so forth. So dependent on different types of application, if you think about your electric vehicles or maybe any vehicles in that sense, you require different levels of the power supply. So that's why not only we need to use AC to DC converter or DC to AC converter, in many cases we also need to use DC-DC converter, okay, in an electric vehicle. And electric vehicle, these are proved to be having efficiency or going more than 80% or even higher, in which the maximum efficiency for an internal combustion engine, that is true for a petroleum based cars, is maximum up to 25%. So they have huge potential, not only enhancing the efficiency but also leading to an atmosphere which has zero emission of carbon into the atmosphere. So moving towards the green globe or green earth mission. The formation and the evolution of electric vehicles is extremely crucial, and in order to do that, the applications of Hemp-based DC-DC converters are also extremely crucial. So this diagram, this is one of our recent work, so in which we are also working on different aspects on the design of a circuit, based on which we are just trying to use our Hemp devices or HFET, whatever you call it, on this boost type of DC-DC converter. So this converter, like the simple operation of it by the name of boost, obviously you should be thinking about raising an output voltage which is actually much more than the input voltage. That's, as you can see, that you are using a lithium ion battery in your car engine, and basically at the load end you need a higher amount of voltage levels. So basically, if you look at the mathematical equation, so you are dealing with the duty cycle of operations of this switching of this HFET or Hemp device, you call it. Okay. So how does it do? Generally, this kind of simplistic DC-DC boost converter, they have two modes of operation. One is continuum or continuous conduction mode, or discontinuous conduction mode, depending on the switching speed and operations you want to have the Hemp or HFET to be used in this particular circuitry. Okay. So when your Hemp device or HFET device is switched on, basically then your source current flows through this L, and this entire source energy of this lithium ion battery is stored in this inductance. Now when your Hemp device is off, then some of the energy which is stored as an inductive energy in L as well as stored in the lithium ion battery, they flow through this capacitance as well as through load. So basically the load is getting an energy which is the value of which is much larger as it was initially there for the lithium ion battery. Okay, and when the Hemp is switched on back again, then this source amount of current flows through L and the energy is stored in L. But at the same time, the energy stored in this capacitance during when the when the Hemp is off, they kept on, getting discharged across the load. So dependent on or not depending on whether the Hemp is switched on and off, eventually load keeps on getting more energy as stored in the lithium ion battery. Okay, so that's why the output voltage becomes much larger than the input voltage that is stored in the battery. And what about the buck converter? So in this case, again, we need the DC-DC operations in which we need to supply a load with a much lower amount of energy which is stored in the battery. So in this case, the positioning, as you could see, of the Hemp devices, the simplistic DC-DC buck converter, the positioning is something different. So now in this case, the source current, it flows through and stores in L when the Hemp is on. Okay, but this voltage stores in in L, we know it is an inductive energy, and while any energy is stored in L, it always acts like the very cause of its generation. So that's why it is mentioned the voltage in L or the VL, it counteracts Vs and reduces the voltage on the load. So even if it starts getting charged due to the storage of the inducting energy, it always repels or it always counteracts the energy which is stored in L, the counteracts the value of S. So basically the charge stored in VL, which actually eventually, supplies the power across load, becomes of much lower value that is actually stored in the source. Okay, so depending on the again switching cycle, one can change with the duty cycle of operation, and depending on that, one can play with the output level of the load, which is or output level of the voltage which is supposed to be supplied at the load end. So this is the basic operation of the DC-DC buck converter. Okay, so the same boost converter that is also mentioned over here, even if it is used to be supplied in a car engine, it can also be used in an energy storage unit. Like we know from the applications of satellites, from solar vehicles, from solar street lightings, we know lots of power electronic circuits are required. And these power electronic circuits such as DC-DC converter, so in those cases, whenever the supply has to happen and then this supply has to be stored or given the supply to either maybe an AC grid or maybe a lithium ion battery or any other conventional energy storage systems. So if we do not use this converter in between, if we directly want to supply from the, let us say, photovoltaic panel directly to lithium ion battery or the AC grid, then sometimes due to the variations in the power fluctuation that may happen in the PV panel, so there may be disruption in the storage sources. So if we are looking for direct charging from PV modules, sometimes it also damages your batteries and reduce its lifespan due to the unregulated charging voltage and current. Because on a daylight, or maybe if you're talking about variations of solar light, depending on the geographical locations of the implementation of your solar panel, or depending on the time in a particular geographical location also, it may vary. So the amount of the voltage that should be generated in the PV panel, they also may vary. And depending on that, there may be disruption in the storage supply unit. So that's why you need a stable unit also lying in between, which controls this kind of disruption. And they should not be damaging either the utility grid in which the power has to be delivered or the energy storage system. So you need a converter or interconnecting system between a PV panel and the energy storage system. So that's why there is important applications of our boost or buck converter depending on the type of sources we are looking for. Okay, so I'll be ending my topic with this final work on the circuit level implementations also, in which we're trying to implement a bidirectional DC-DC buck boost converter. Okay, this is the Proteus like PCB design based on the Proteus software, and this is the final product which we are trying to achieve on a PCB platform once the circuit design is finalized. So these are the typical applications of two different Hemp devices, and the earlier diagrams also we have seen. And a microcontroller we have implemented on the Proteus, so that depending on the pulsed width modulated signal that one can generate out of this microcontroller, so one can toggle back and forth between this bidirectional converter to work it either as the buck converter or the boost converter. So finally, like we are trying to use a positive PWM signal, and we are trying to use this particular, like we have started working with this ICL7660 microcontroller. So the typical diagram of it is also shown in this case. So I'm not going into much more details into it due to the time constant, rather we should be having a discussion of it. And this is the typical working of these converters. Like we can separate out our input time signal that is applied across either HFET1 or HFET2 or Hemp1 or Hemp2. So what it is said, like during when, for example, if you start to think that your device is actually based on its operations, that at one value of voltage, if it is 0 voltage repeat, if it is switched off, and at another level of voltage, like here the example is given like at 5 volts roughly, the device is turned back on. So depending on that, we have tried to give you a schematic of the time interval. So T0 to T4, we are just trying to show you and to give you an idea how this bidirectional DC-DC buck boost converter works. Okay, and whatever the time signal or that is generated by the microcontroller PWM signal, obviously, how like whatever signal it comes at HFET1, it is obviously opposite that is applied across HFET2. So in the transition at the interval T0 to T1, HFET1 goes off, but HFET2 goes back on. So in that case, this L is getting charged, what is actually shown by the arrow marks. And the converter works in the boost mode, as we have already understood that the motor has to be supplied, so it is working in the boost mode. Okay, so in this case, whenever you are talking about T1 to T2, then in this case, HFET becomes on and HFET2 goes off. And then it is slowly, as this like the converter output voltage is applied across the motor. Now, as this converter operates in the boost mode, it is capable of increasing the battery voltage to run the motor in the forward direction as well. What happens when we are transiting from T2 to T3? Then HFET becomes on, HFET2 goes off, and it is slowly transiting towards the buck mode. And T3 to T4, the final one, when HFET goes off and HFET2 goes on, battery is charged again and the converter operates in the buck mode again. So depending on the PWM signal of operations and depending on how well we can do microcontroller programming, we can play with the number of different control units, as you could see for these cases. And we can design such kind of bidirectional buck boost converter, which are very essential for this electric vehicle operations and energy storage applications. So I am ending my topic over here just to have more discussions on it with all of you, so that we can get to know more about each other and think about avenues in which we can work together as well. And just to end up my topics, so there are avenues also, like if you are interested to learn more about our work, because many of these things specifically to Hemp devices, which we are not able to disclose at this moment, because many things are currently being pursued by the students, and many things are also under review mode in different journals as well as in patents. So few things we tried to give you some pictures, but unfortunately would not be able to share with you everything at the current moment due to the confidentiality issues. So if you have more things to know about this particular topic or any other topic that we are covering in our research group, you are more than welcome to contact me. You can drop me an email. You can also check our website. I think many of you might have done already, but if you have not, you can go through my websites. And if you are interested to get associated with us, there are avenues also. Our institute has provided a provision for students and faculty members from outside of IIT Indore also to engage with us for the online research. So currently, many faculty members and students are associated and currently also pursuing their online research with our research group. So if you can refer to our research website, you can get actually their information. So we keep on updating our website every now and then. So as of now also, you could see the informations about the students and members who are doing or pursuing their online research work with our research group. So I'm just ending my topic over here, and I'm happy to discuss with you further.
Thank you, sir, for such an informative talk. Now, participants, now floor is open for the questions. You can unmute yourself and ask your questions. Any question from participants?
Good morning, sir.
Yes, good morning.
Sir, I am working on the development of supercapacitor electrode active material.
Okay.
I want to go for next step. Just I want to know that what should be the next step to develop final device for practical use.
Yeah, supercapacitor we have not been working, so actually I do not know much about the supercapacitor. So if you are kind enough, could you please let me know about the geometry of supercapacitor and basically what actually you are trying to do if it is not that confidential?
Generally, the two electrodes for energy storage device, just like lithium ion battery. I'm
You are
using.
trying to change with the dielectric constant of the material so that it can store energy.
Yes, I'm
Is
developing
that correct?
that can store high energy.
Okay.
Generally, lithium-ion battery has higher energy density, but low power density.
Yes. So have you done anything towards the basically translational type of work, or you have just developed the material and by measuring, I don't know what kind of calibration, electrochemical, I think, yes, you do probably plot some hysteresis loop or that kind of, if I can figure out.
Yes, sir.
And by cyclic voltammetry measurements, you are saying that this is much more useful. But have you tried to see that how actually energy is stored in those devices whenever you talk about, because lithium ion battery is already practically implemented and commercially these are made available. One can buy. So have you worked on the practical implementation level point of view?
Yes, sir. I have developed the electrode material that can charge just like a 3-4 red LED of 1.5 volt for around. If I am charging for 30 seconds, it can discharge it for around 2 minutes. So this is not sufficient for the practical application.
Yes.
So just like this electric vehicles, I want to develop the material to be used in these electric vehicles.
Okay.
So in that respect, I want to develop the final device.
Okay. And which area you're trying to actually target? You're looking for applications in electric vehicles?
Yes, sir. Electric energy storage device of that material. It will be used like electric vehicles or many other areas in that the energy storage device is required.
Okay. Fantastic. So as of now, do you know the energy storage? Like, do you have any technical parameters? Since you're aiming to be an energy storage device or system, so
Sir,
what kind of technical parameters, like if you look at the commercially available lithium ion batteries, so you should be knowing what are the technical parameters in those cases. So
yes.
dependent on that, can you also share what are the technical parameters?
Sir, as
Because
of
whenever
now,
we are trying to couple the energy storage with, for example, here I share with the boost or buck converter, we just have to see what is the power rating and what is the maximum amount of current the energy stored storage device can supply, and what is the level of passive circuit elements need to be added, because you have seen the application or usage of inductance and capacitance. So all those parameters and technical features are required to be known. So for your system, what are the technical parameters you may have? Like, you can check and tally those parameters with the energy storage which are commercially available.
okay. Sir, as of now, my material can charge like small devices like calculator and small that watch, electronic watches. But I want to develop the material for this heavy vehicles like electric vehicles.
Yes. So that is what I'm trying to say. So if you want to do that, first you need to give an technical parameters. And then probably, so first what you do in the lithium ion batteries, which are like electric vehicles have already come into the market, not
Yes,
not in India probably, but it is available. If you search in a Google, you will be also able to find out.
yes,
So you
yes,
can see the energy storage ratings, power ratings. So
yes.
if your system can also give similar amount of ratings, or how low or how high it is lying in comparison to those, so from there you'll be having some estimates. If you are there, then definitely it can be coupled with the Hemp devices, or maybe rather in that sense any, because these buck or boost converters also, these are also readily available in the market. It is the
Okay,
simply connection and playing with what kind of efficiencies you're trying to achieve from these converters.
okay, sir.
Yeah. So if you're interested, you can also drop me an email regarding this, so we can also work on this project to see how beneficial will be your systems if we are thinking to couple it together.
Okay, sir. Thank you, sir.
Most welcome.
Any other question from participants? Okay. If there are no questions from the participants, let's thank our speaker. Thank you, sir, for the time and effort
Thank you, Sumit.
to share your experience with us. Thank you, sir. So next lecture will start at 11:15. Tea break. So we are taking a short tea break. Please, we will meet at 11:15.
So I guess today is the fourth day of the program.
Yes, sir.
Okay, that's great. So this talk, what we will do is I will initially give you a little bit of idea about what we do in our research group, and then we delve into um, application of optics that we are working on, and specifically we'll look at visible light communication system. So if you let's say know, or if you don't know what is VLC or Li-Fi, we'll come to that. And initially, I'll try to motivate this from the application point of view, because this is something which is it's no longer, let's say, a blue sky research. It is coming to our homes, buildings, other places as well. So let's first start with a small, a brief introduction um, about the group. So the slides are just loading at the moment. So yeah, let me share this one. Okay, so yeah, share. Yeah, okay. Okay, so can you see my screen? Yeah, okay. I'll make it full screen. Okay, so you can see it full screen, right?
Yes, sir.
Okay. Okay, so yeah, so I'm Professor Vimal Bhatia, currently with Department of Electrical Engineering and Center for Advanced Electronics at IIT Indore. Also adjunct faculty with Bharati and Bharati School at IIT Delhi and Triple IT Delhi in Department of ECE. On this, I mean, the work that we do is along with our group members, as mentioned below, mostly our PhD or PG students. Some of the work that we have been mostly involved in is on performance analysis of beyond 5G communication system, adaptive signal processing, machine learning, and deep learning algorithms for 6G and some biological applications, where again optics and as optics, physics, and signal processing they come together, or machine learning come together, is something that we have looked into for some of the societal challenges, like looking at viability of a seed or not. So that's where we find uh, the application of optics as one of those very important. There's some of the protocols from ECE background you might have heard about OFDM, MIMO, and then visible light communication system for 5G and 6G. That's what we'll be covering more in detail in the talk today. Then we're also looking at optical and quantum networks. So that will not cover today. We'll not go into the optical networking side. So here more focus will be on IoT and those kind of applications, mostly indoor applications. Then we also did one thesis on radar signal processing, and we always look forward to providing some solution for industry and defense. We have active collaborations with researchers from the UK, Ireland, Norway, Finland, Czech Republic, Canada, South Africa, US, and external funded mostly from DST, MIT, UKRI, AKA Finland, ISSTF, MHRD, and others. And currently we have a projects going on with the US on quantum, recently got approved. Then with the UK on machine learning, and Finland on machine wireless as well, also recently got approved, that one. We have about, this is slightly dated. So we are about 130 plus journals and 149 conferences and all, and a few IEEE journals. Most of them are IEEE journals. And then we currently have 4 patents granted. It's a little bit dated slide, and about 10 book chapters and thesis submitted, and mostly, and some of the previous students, they have received best conference papers, and most of them are our colleagues now, working in IIT and ITs, triple ITs, or doing postdoc across the world. So I'll cover this one in more in detail on visible light. So I'll not go right now in detail, because the rest of the next set of slide deck is purely on visible light communication systems. This is a work which we do on heterogeneous non-orthogonal multiple access for 5G and beyond. So this is an upcoming modulation scheme that is, I'll say multiple access scheme that is coming, which is again because of advances in compute and our need to have many of these devices, like IoT devices being connected in the close, vicinity. So as per one of the latest reports from Cisco, we were about, if you go back around 2008, 2007, around that time, we were about the same number of humans on the planet as the number of devices. Now, as you move forward. So as you stand now, this is around 7 to 8%, eight times more number of devices than the human beings connected to the internet. So they are now we are in the IoT era where a lot of devices are connected. So we will so this is one of the techniques that we have explored, NOMA, non-author multiple access. This is applicable to, in fact, our first paper that the journal that came out on TCOM was on applying NOMA to visible light communication systems. Then this is another application of optics. As you see, optical communication network. So our backbone network. So we can't really have a, if we look at end-to-end system, then we need to look at optical networks as well, because a lot of our data flows through these optical networks. Now we are getting even these optical cables in our homes as well being connected. So there's a lot of optics around, which is carrying huge amount of data. The submarine cables are through optics as well, and proud to say that a lot of the majority of these submarine cables, or most of them, are actually owned by and run by Tatas across the world. So this is a very important feat for us, and we see that these are coming to our homes as well. So now our homes as well, we have optical network cables. So here we have worked on various aspects, like if let's say there's an earthquake or some other thing happens, then there's a risk, or even there is a territory which is, let's say, not very friendly. We could look at some routing schemes so that it does not go through those. And recently we have moved this over to look at quantum key distribution, more efficient one, because at the end of the day, we will like to have the same optical fiber um, carrying keys and the information and the signaling part as well. So because laying another set of fiber is very difficult, very expensive, requires a lot of planning. Whereas setting up a wireless network is easy, it's fast, it's quick, but doing for optics, you need to do a lot of digging. So there was a lot of planning. It's very expensive as well. So our focus here has been on looking at how we can incorporate the quantum key distribution to make these networks more secure, while trying to use the same network that we already have. And now we are like moving. So we did some initial work. Now we are looking at how resilient they can be in QKD transfer, because there are certain peculiarities about these which we need to look into. We'll not go in detail again here. Then this is the other part, which is a performance analysis of multi-hop network. So here we all of us might have experienced this, that you go inside an office or a home, and inside the cellular communication signals are not there, or they're very low, with a very low SNR, so you can't really do any communication. So this is one scheme that's on the top right corner. We see that there's an optical fiber that's coming to one of the nodes, which converts from optics to RF to probably to a millimeter wave, like a indoor type of environment. You have, let's say, a Wi-Fi router, and then from a relay, which is in one of the rooms, we convert to a different frequency band, which goes to UHF, which can cross across the wall and then go to another relay called R2. We call them SUDAC because they are like converting from one band to another. So this is the full form for it, but basically they are converting from, let's say, UHF to millimeter wave or vice versa. And then I'm in this next room as well, I'm able to communicate when it converts back to millimeter wave band. So now we've done some performance analysis of this network, and also looked at some of the practical issues that we get, because around 90-95% of the research and papers in this area, they usually the researchers assume it's a perfect channel, perfect communication system, but in practice there is nonlinearity, and we find this in optical networks as well, which we'll cover in the later part of the presentation. So now here we have looked at some theoretical results where again I have a multi-hop network or a relay type of network, cooperative network, where there's multiple relays. They all have a amplifier in it, and then they are forwarding the signal. But because of the nonlinearity of the system, the bit rate that we expect, we don't get exactly, because again, high power amplifiers are nonlinear. Similar thing we see in the optical networks as well in our IoT setups, where I'm using visible light communication system. There, we know the semiconductor devices, LEDs, they are non-linear. Right. So we want to know from this analysis is, what if I have, let's say, a nonlinearity of a certain shape, what kind of rates that I can expect? And what is the impact of it? Because usually in theory, I can say with a linear amplifier, I'm getting, let's say, 1 in 1,000, 1 in 10 to the power 6. Let's say the symbols go in error. But by using a non-linear amplifier, what is the impact? How much loss we incur? And that is actually a more practical value that you will achieve. Okay, thanks. So I'll move on to the our topic in detail now. I'll change slides here. If you have any questions about this, then feel free to ask. Press some button. Okay. If I say don't save. Okay, so let me switch my slides. Okay, yeah, this is gone. So now I have a PowerPoint. Okay, so you can see the set of slides, right? You can see the new set of slides. I'll make this as full screen. Okay, sorry, it will be in the view mode. Okay, so now let's look at this. So part of this I actually had presented in the WWRF conference just a few days back as an invited speaker for again applications of visible light communication systems, because there's a lot of interest. So this was held in Paris for 2-3 days in early December, where again they're looking at from the regulators point of view, they're looking from the band's point of view, and there is a feeling that now it has come to age. This research is going to now come to the real life. So let us look at what is a visible light communication system and why there is a need actually to exploit these. So a VLC or visible light communication system has emerged as a promising green and interference-free supplement to RF-based systems. So in case of RF systems, there is the energy required to transmit is much higher than that is required in case of using visible light or using LEDs. It is green because we are more energy efficient, we can say, because it is actually using the a very low energy, and we are using this energy anyways for transmitting or illuminating for illumination. So if the same can be used for communication, that serves our purpose. So visible light relies on VLC relies on intensity modulation of light emitting diodes according to the input message. A very crude example of this is our infrared remote controls that we have been using to control our devices for switching on television, changing the volume, changing channels, and whatnot we do. Then our air conditioners and others. So they all are driven. And initial car keys were also by IR driven. So here, this is, you can say, a more glorified form of that. It is going to be looking at covering larger download speeds and larger areas like mobility. And so there's a lot of other things. It is more closer to the Wi-Fi that we're trying to get, but using visible light communication system. So here visible light covers a wavelength from 380 to 750 nanometers. That's a huge wavelength. And if you look at this spectrum, we start from, say, the right hand side. We look at the AM, FM, TV bands, then we look for radar, then infrared, and then we come to visible light. And as we talk about the coming of 5G it's already started in some places. Here also, hopefully in India, will be able to. I think auctions will happen next year sometime, and after that the services will be there. So in probably a year or so, we'll start to see there. So there we are looking at some of the early initial bands of millimeter wave, and then moving forwards for 6G or 7G, we are looking at our discussions are going on to explore terahertz. And after then, that's the last of the RF band that can be explored for communication. We are going to move to the optical bands thereafter. So we are already working in visible light communication systems. So this is, as I said, technology is coming to age. So it has a very high bandwidth, which is always a good thing for communication systems to have a high bandwidth, because if you look at the cellular networks, we are really struggling to get a good band. Good, first of all, the carrier frequencies, and then contiguous band is a struggle to get. And in the cellular network, they go for a license fee which is very high. So you would have heard about 3G, 4G licenses. Now similar thing will happen for the 5G licenses. They go at crores of rupees. They're actually the most expensive part of a telecom network, which is a fee that the government levies on the operator. So ATAL, Jio, Vodafone, they all will pay a fee for a certain region and certain bands. Now here in visible light, the bands are huge and they're also non-licensed. So what does that mean is, so you don't really need to purchase a license to start transmitting. So for instance, if I'm looking at, if I take an analogy from our Wi-Fi networks, so they work on a ISM band, so instrument and scientific measurement and medicinal use band. So those bands are available for free. You can transmit in those bands without purchasing a license. And of course, you have to be within a certain decibels. So it is, it's okay for human beings. But this is, but they're operating in the unlicensed band. So I don't need to purchase a license. At home, I can create my own transmitter by purchasing this 1,000 rupees box, connect it and start transmitting. Whereas for a cellular network, we are not allowed to transmit legally on things unless you are a licensed user. So you have taken a subscription, you have taken a SIM card from a subscriber, you have paid the fee, and then you're able to transmit on those bands. So I cannot use SDR or some other device to actually start transmitting. I can receive. Receiver is not a problem, but transmitting on those bands. So visible light communication offers us communication in, first of all, the advantage is high bandwidth. Then there is no license fee. Right. It's low cost and easy implementation, such as using the existing lighting infrastructure. And we have seen in the last decade or so, our lighting infrastructure has slowly moved from incandescent to LED. So in most homes, offices, common places, open areas, we are using LEDs for lighting, using LED in our vehicles as well for lighting. Front and the rear lights are coming in as LEDs. So it is again, it's low cost and implementing, because LEDs, you can purchase a set of LEDs for a rupee or 10 rupees. It's very very cheap device. So it's easy to get. So it's easy implementation. However, if you, let's say, want to do a RF communication, so for that you need an SDR or a transmitter tuned to a certain frequency. So the energy is also high, and you need to have a separate unit. But here we are saying, because LED lighting is already there, we can possibly use the same infrastructure. Then It is energy efficient. As I said, it is going to use the same type of energy. And we know that initially when our lighting, or even now, the lighting infrastructure is talked about, it is primarily um it came because of the energy efficiency we are getting as compared to the incandescent uh, bulbs and lighting. So it is green, it is taking less energy, but giving us the same light. And if I can use the same lighting for communication, very well. Then it's immune to interference from EM waves. This is so if you are, let's say, traveling or in a block of apartments or some place which is very close communities, so there physically, then you would get a lot of these Wi-Fi um, transmitting. So they all are in a way interfering with each other because they're all transmitting in the same band, same ISM band. Although okay, there are protocols to try to avoid them, but still they are doing it. And if you go above a certain number, then very difficult to have interference-free transmission. So there is a problem in electromagnetic sources, and most of the noises that are created from the environment are also electromagnetic in nature. Then or the effects that we see from the cables or starting off a vehicle, they're more electromagnetic. Then so this doesn't affect visible light communication system. So one part, of course, there is not much devices available. Other part is from the the next advantage is high security of visible light. So visible light communication cannot, so visible light cannot cross an opaque boundaries, right? So if they cannot cross opaque boundaries, then they are secure in nature. Again, the interference is also low because RF can penetrate through the wall, but this cannot. So visible light cannot. So in a way, it provides an inherent security and also immunity to the interference. Of course, if let's say you have a window, so from window the signal can go out. But again, if somebody tries to eavesdrop, then they would be somewhere closer to the windows. You can possibly see them or something. So it's still it's inherently a secure type of communication system and very low interference. Then there's a threefold goal. So it basically provides, in summary, illumination, communication, and energy harvesting. So we could, and there are certain test beds available where we are harvesting this energy. So you are trying to, and this is very important for an IoT type of application, where let's say you have some sensors which are no, going forward, we're looking at sensors embedded within the buildings, or let us say the sensors are somewhere out in the field for precision farming. Then these sensors need to be powered, and you may not have the luxury of having this, grid power or the power lines being connected to the LEDs. So that luxury you don't have, right? In certain places. So there we need to harvest the energy from the environment. So we know solar panels has been there for many years. So the same panels can actually be used as a receivers as well. Or we can have some photodiodes, which will harvest energy, and harvested energy will be then used for decoding the message and maybe transmitting it over the network as well. So these are certain new designs that are coming. So this VLC provides us both illumination, communication, as well as energy harvest. So it's a green and everlasting source. So, now, another advantage with the visible light communication system is that there's a high signal to noise ratio due to high illumination levels provided by the LED. Because when we're doing communication, we require higher level of uh, power from the LED. So we are working already in a high SNR region. Some of the applications are Li-Fi systems, smart lighting, safe for RF sensitive areas like hospitals, aircrafts, intelligent transportation system. As I was telling you that now we have our there are some deployments we're looking at in some of the latest cars to use the LED in the front of the vehicles for communication. LED at the back could be have a photodiode, and again can be used for communication. Also, so vehicle to vehicle communication can happen. Then vehicle to infrastructure, the traffic lights, they would have a visible light communication enabled lighting. So they can transmit some information like how much the traffic or the weather conditions or some generic information can be uh, downloaded or coming from the traffic lights. Or when, let's say, for autonomous vehicle, if it turns green, it can also send a signal that yeah, it has to start the vehicle. Now, IoT applications are quite a few. We'll cover some. And then wearable devices. This is a new area, again, based on IoT, Internet of Things paradigm, where there's a lot of sensors in these wearables. They're used for monitoring, your movement, your BP, sugar, and other aspects. We are using oximeters and also all built into a small wearable device, which is a very good example of an IoT device. It has a GPS and a lot of other functionalities in it. So this is what broadly are the applications of visible light communication systems. We're looking at personal area network, where in conference halls I have lighting that can, transmit data. And these are some of the early application and deployments as well. Then there's a transportation hub, like in railway stations or within the airplanes. Visible lighting can be used for small areas, so personal area network. Then home and offices, again lighting from the top. We may not need RF, and again there are certain and use things we hear about RF, and we should not use too much of RF. So visible light plays an important role. Then data showers like this, they can be installed because if you have lighting in the street lighting in many of cities, we have them, and they can be used for transmitting data as well. So you can provide free Wi-Fi. Then intelligent transportation system, as I said, vehicle to vehicle communication, vehicle to infrastructure communication through this lighting or stop signs or traffic signals. Then non-RF friendly environment like mines, working in chemical plants or refineries, their optics based communication is preferred. Then EMI sensor, like in hospital and other areas, like even when you're flying in an aircraft, you're told to switch off or put your handset in a non-transmitting mode. So basically, you're not transmitting any RF signal. So for those safety and for children and other things as well, it's better to use to avoid RF as much as possible. Security, of course, I've already said. It is also being exploited very much for the underwater communication system. So this is another very interesting application that is there. Now, as an indoor positioning, that is one example I can show you, or you can go later. You can note down the link and see it later. It's in shopping malls where indoor positioning is key. You can share. You can make a shopping list, and then it will guide you where the goods are. It can give you latest offers, and it also knows where it is. So indoor positioning and very accurate positioning can be done through visible light communication system. Again, augmented reality, because again there's a lot of data that comes with entertainment. Again, lot of data speeds can be there. We can do gaming stuff. Then for short range communication systems, so it could be a replacement for cables. So between the devices communication, it is easier to do. So in RF world, we are still discussing about device to device, but here it is easy to do. We are in a way, when I'm controlling my television or an air conditioner, and when it gives me the feedback, in a way, I'm already doing a device to device communication there. A very good or simple form, but that is also possible. So what are the major companies in this area? We have first is the Pure Li-Fi, one of the biggest VLC companies, founded by Professor Harold Haas at the University of Edinburgh in the same research group ITCOM. So he has a company which is working for many years, and is one of the largest ones. Then Firefly Wireless Networks is again a VLC and infrared company. They're jointly owned by Light Monte, I think a French company, communication company. Oralcom, again a French telecom giant working with Paris and Claire on Li-Fi devices, and VLNcom in the States working on developing products with this. And some of the other ones which are there is Signify, Efficient, Lucid, Lightbee. These are some of the newer ones. But then we have Wipro, Panasonic, Philips, and others. So what we are seeing is in the lighting industry, a lot of the companies which were involved in the lighting are now moving towards the Li-Fi network. So that's like a new source of revenue or a product stream for them. So here we have, so they had an issue basically as you move towards LED lighting. So slowly, okay, everybody started to move to LED, but LED lighting also is more robust. They go bad less often than the incandescent light. So replacement is not happening much. And especially in, I would say in the Western world and here also, where power supply is mostly, you know, of a good quality, good voltage level. So they're not going that bad. Although applications are increasing, but the replacements are not happening much. Right? Now, for them, visible light communication is another business stream that they're getting it. So we see Wipro, Panasonic, and then Philips and all getting into these visible light market. Now new Li-Fi products are getting launched faster than ever. A lot of companies are working on developing Li-Fi solutions, improving Li-Fi technology. So Li-Fi Max, My Li-Fi bidirectional LED. So look at some of these examples. So My Li-Fi is a desk lamp. So these are products which are available that you can get. Now each user can connect to the internet through optical signals emitted by the tabletop desk lamp. Then up to 7 connections can be done similar to our Wi-Fi network. And it provides a transmission speeds up to 23 Mbps for downlink. So that's huge. And it's just a simple light lamp, right? The Limax, this is the one that you can put on the top of the ceiling. And they look more professional lighting as well that you can put on the top. And there's a small network cable that can go in. So they are very fast for 100 Mbps and compatible with various devices, and you can connect through USB and other operating systems as well. The Li-Fi Care is being used for a medical thing where, let's say, RF is not permissible or radiation-free areas. Now, Pure Li-Fi came up with this dongle type of device so that you can connect with your laptop and start communicating. This is compatible with Windows 7, 10, Linux, Mac, other operating systems. Download speeds up to 42 Mbps can be achieved. So this is similar to when we started to use, let's say, our cellular network, so 3G onwards, 3G, 4G onwards. We initially had these dongle devices to connect to the net. A similar thing is happening for visible light as well. So Pure Life has come up with this solution. And eventually, hopefully in the future, our laptops will be having a panel for communication with the in the visible light domain. This part of it I already covered. So this is another product. Basically, vehicle secure link or Pure Firefly Li-Fi. Sorry, so this is a setup here where we have cars talking to each other or through the traffic signal. So they are communicating as well as illumination is there. And secure office link. So within the office, you have lighting from the top. So there you have laptops communicating with the top there. And then we have Ultra HD television sets connecting with the visible light Li-Fi systems. And these are some kind of panels that you can purchase and install. They cover up to 400 square feet, which is good enough for a large medium-sized office space. And can support up to 70 Mbps downlink and 60 MPS uplink. So these are commercial products that are right away available in the market. So you can go ahead. So there was some test that has happened in different parts. So this is in Orkney Island in Scotland, where the Pure Li-Fi Center with the 5G rolled first support from different agencies. I did a small test where you can use FSO backhaul system for connecting rural and remote areas. Now, it was sort of okay. There were like 389 rural towns, one of the slowest bandwidths we're getting in the UK, and connected this through this test to University of Edinburgh and Pure Li-Fi and other council and other companies to execute this project on 5G rural first. This is another thing which has come from the 6G flagship. They also made a demo here. So you can visit this link if you want to note down. I'll pause for a minute. Or you can take a screenshot. So this is another thing. You can go onto the YouTube and look at this video where again the visible light communications used for in practical settings. Again, this is driven by Dr. Kaz from Olu University. They're using it for, again, as a supplement for mixed RF and visible light. So let us say, because again, there is a sort of limited mobility, or let's say when you're moving from one room to another or one floor to another, in that case, we expect the RF part to take over. So there'll be some kind of handshaking, but it is looked at so his team has looked at from the interoperability of Wi-Fi and the visible light systems. Then this is a product by Philips. You can look at this. This is again a small device connected with Pure Li-Fi. So they have a lighting system, and they use Pure Li-Fi's dongle to connect to your laptop or a tablet. So you can note down the link and have a look at this. The world's first Li-Fi office. So they have done this in Lacadas, which is a big real estate company's office in defense in Paris. They have demonstrated an uninterrupted Li-Fi connection in presence of natural lighting and also user mobility. Then there's this one is a Hegel gym in Stuttgart in Germany, where they have Fraunhofer has done a prototyping of Li-Fi systems in the school gymnasium. Similarly, in Kyle Academy in Scotland, again, Pure Li-Fi from University of Edinburgh has done this setup there for connecting the using Pure Li-Fi and for communication in the schools. So again, a small dongle, and the person telling the student is Professor Haas, who is the co-founder of the Pure Li-Fi company. Then there's another one that's very interesting. You can visit this is on Carrefour. It's a big, it's like our big bazaar, D-marts and all that we have in India. So Carrefour is a big retail giant where they have installed Philips LED for visible light communication system, where they have developed an app. So you actually don't need another device, you don't need a dongle. So our phones itself, when they can you install the app, and to the phone screen, it will communicate with the lighting above, and can direct you to where the food, make a shopping list, can direct you there, or it can tell you the offer. So you can note down this link and look at this video later on. Very interesting application, and these are some of the real applications. So that's what I said, visible light communication system, it has been researched for over 10 years and more. And I mean, basically it got steam in the last five years, and then now it is coming to the masses. It is already there in different products. So as I'm telling you that this is some of the, you can do a shopping list, you can do stock verification and things using this. And because Li-Fi has a good localization much better than RF. Um, this can get you close to the actual product, give you the real picture of the situation there. Now, not I know says all the good things about it. Now let's look at what are the issues with this. So I said LED has a nonlinear behavior. Now this impacts severely the performance of a visible light communication system, because that's primarily dependent on the LEDs for transmission and reception. Then intersymbol interference. This happens due to time dispersed nature of visible light communication system. User mobility, that leads to multiplicative fading and this. And then there is a because people are moving. So like in this case of a shopping center or in homes, you might be okay moving a bit less, but then in case of office space, you might be moving, giving a presentation, so maybe you're moving around. So those there's some less level of mobility involved there. But whereas if you look at vehicle-to-vehicle communication system, there is mobility already there. So there we'll look at some different solution, and that's where I have Anubhama, if the time permits. Anubhama will show you the PhD student will show you a different type of a system, which is more apt for high mobility type of system. So we are looking at ways where visible light can be extended for high mobility applications as well. So now, yeah, so we were here. So let's look at this application of LED. So another application I forgot to mention, that there is deployments or testing are already going on for having visible light systems or Li-Fi system being done by pure Li-Fi in the future airplanes. So where within the airplanes, you would have a connection from visible light communication system for your entertainment systems or others. So you could use your mobiles or other devices there and using visible light. So it takes away a lot of the cabling that goes on in the inside the planes for entertainment purposes. So okay, now let's look at these issues that we get, because and also, yeah, there's another application where Disney is looking has incorporated visible light communication in their some range of toys. So they're all, again, at the end of the day, are IoT devices. They're very small bandwidth, but they're working on the visible light communication. So optics is there too. Now let's look at the issues that we see in visible light communication systems. So one of the significant one is the LED nonlinearity. The issues that we saw before, they significantly degrade the achievable bit error performance. They cause significant performance gap between the promised and the achievable rates. And that's what, it's like from a customer point of view. If let's say somebody tells me, 3G, 4G, I would give you 100 Mbps. I don't get 100 Mbps on my handset. I don't get 10 Mbps either in most times as a download speed. So there is a gap between the theoretically promised ones and then what you get in practice, because there's a whole full system involved there, and it's not an ideal condition. So considering that, similar thing we get in the visible light communication system as well. So we need to, so this is a very important aspect to be looking into. So we can give some realistic figures that, okay, of course, you may not get, let's say, 100, but you might get 50 if you use one of these new designs or algorithmic implementations. Then the throughput of the existing VL system can also be increased by using massive MIMO. So this is a very important, I don't know if you have come across MIMO or not, but MIMO basically means multiple input, multiple output into the wireless or a communication channel. So what we have seen in the later 1990s that MIMO started to come in, and in RF in our laptops, and we are now seeing them. Our handsets still lack MIMO for cellular communication system because of the size and the compute it requires. Whereas for Wi-Fi, yes, we can do MIMO. We are doing MIMO these days. So basically what happens if you do MIMO, you are having multiple and multiple output. You're having this multiple independent streams of data. So you can think of it as, let's say instead of just one cable uh, from one point to, from source to destination, you have 5 of these cables now. So they can transmit all in parallel. They can all do communication in parallel, and your data rate improves by 5 times. Similar thing we can do in wireless domain as well. Again, given certain conditions, it is possible by using multiple antennas. In case of visible light communication system, if I take an analogy, our LEDs, the LEDs are our transmitters, and photodiodes are our receptors. They are again so LEDs can be taken as antennas, and on the receiver side, I can take photodiodes or even solar panel as an antenna which is receiving this. So, and one advantage with visible light communication system is that if you look at our lighting infrastructure, if you, let's say, by any chance open up one of the bulbs, LED bulbs, you'll see a grid of 8 or 16 of these LEDs transmitting. And so inherently there is a MIMO structure there. So if I consider all of them to be an independent things, so you can. So similar thing, yeah, similar thing with the tube light as well. So you have these set of LEDs, so they can all be considered as independent antennas. So you have MIMO as an inbuilt feature, but if you talk to someone who is working on MIMO or some a device level implementation or doing it on an FPGA, they would say it's just not, it's very difficult. I mean, it takes a lot of power. It needs a lot of physical space on the chip as well. So it's very difficult to implement. And okay, research would be talking about massive MIMO, looking at hundreds of antennas. So it is not physically possible to have hundreds of these RF chains. So there are certain techniques that are being used, but still very difficult to get to that 100 mark. Even there's a few deployments, but very difficult to get to those marks. But then the energy requirements also goes very high, so very difficult. But whereas in VLC it is already there, it's very simple to implement. It's already there in any deployments. But the problem with that is the massive MIMO is that the channel is ill conditioned. So this 3 bars that you see, it says ill conditioned, basically ILL conditioned massive MIMO system, because these LEDs are very close to each other. So the condition number of the channel matrix is not it's not conducive, because there is lot of it's not because they're close to each other, so there is interference. They're not any classic. They're not actually independent of it. So there is a correlation exists between different channels, and inversion of that matrix, because at the receiver, what I try to do is try to do inversion of the channel. It's called as equalization. Now, if I do the inversion, then for ill conditioned channel, I will be, if I use, let's say, first of all, I have to do a matrix inversion, which is a very difficult thing in practice to do in real time. And if I'm able to do, then it results in noise amplification, which degrades the overall bit error rate performance. Because at the end of the day, in a communication system, I'm interested to have a very low bit error rate. So what does that mean is, if let's say you have how we measure it is we'll have let's say I transmit 1000 bits, and then one of the bit is flipped. So from 1 it becomes 0. Then I'll say, okay, 1 bit is an error out of these 1000 bits. So I give, okay, 10 to the power minus, so 1 cross 10 to the power minus 3 will be my bit error rate performance. So the bit array performance degrades because of these nonlinearity and other factors. So what we have looked at for different applications is looking at pre-distorters and post-distorters. So pre-distorters at the transmitter, they would do some kind of a you can say prefixing of the channel, because I know I'm using LEDs, there is nonlinearity. So can I do something in the pre-distorter? So there like in communications, you might have come across companding and this expansion and companding. So that is the same phenomenon, philosophy here, where we try to design a pre-distorter which will distort the signal in certain way that when it goes past the LED or the transmitter, it will be smooth or a flat faded signal. So the negative effects of the LED, the nonlinearity, are mitigated through some pre-distortion. Then at the receiver, or alternatively, alternate design is to do it at the receiver. So when the symbol has been received at the receiver, what was transmitted, I can use some kind of a pose distorter to correct this impact which has happened in the channel, or there's nonlinearity, there's noise, that can all be fixed at the receiver by using pose distorters. They're also known by the names of equalizers, very commonly used term. So this is the equalizer for a communication channel. So now these are some of the very early works which are given. So we can use a lookup table type of solution. This is easier because what you can do in theory, if you have a LED from a certain manufacturer, you can get their specification, and then you can design a lookup table which can do this pre-distortion or a pose distorter, because you already know what kind of nonlinearity there is. You can have these coefficients already calculated in a lookup table, put them in a memory, and can read from the memory and do the filtering part. But this is a very simple solution, easy to implement, but it's not suitable for modeling dynamic changes in the system because it is fixed. And tomorrow, let us say you are changing the transmitters. Let's say you change the bulb, then again the characteristics might change. So this is not really, because it's a fixed type of a solution which can be incorporated, but very quick, easy implementation to have. And we have seen from our research is that it's still better to have some kind of a either lookup table or LMS type of this, which is in the next one. So they use adaptive NLMS, normalized LMS algorithm to track the nonlinear behavior, and adaptive algorithm. But even if you use a simple technique like a lookup table, still you gain a lot. Even if you use a LMS based one, which is here, which is still you gain a lot if you don't use any technique to fix this nonlinearity. Then this one given by Kim, reference number 7. So here this delivers a suboptimal performance as LED characteristics are nonlinear. So that we tried in one of a very early work on. So this is the one which is in PTL, Photonics Technology Letter, I think way back in 2014 or 2015, where we looked at this type of structure, a Chebyshev LMS based structure, because we found that LMS is good, so least mean squares is good, but if you use Chebyshev type of structure, then it performs far better, because Chebyshev structure will try to model this nonlinearity much better. And we also found that you don't have to really go to a larger order. I think it was to the order of third or fourth order, or even lower, second order. It worked very well to circumvent. So I think it was third order, fourth order. Now this relies on the perfect feedback of detected symbols as a transmitter. So that's one looking downside of it. However, perfect feedback may not always be available in practice. So we then work on the pose distorter. So this was a pre-distorter. Now we can work on the pose distorter, because if I have a pre-distorter, I need this information about the channel model, which may not be available fully. There will be some estimation errors, and when this information from the receiver is transmitted to the transmitter, it is usually quantized. So there is still an impractical system. So we don't have a real or very close estimate of the channel in practice. So that's why pose distortion might be a better option, because you don't have to do this handshaking and transfer the information back to the transmitter. You can do everything on the receiver itself. So here, other works that we have looked at is looking at the receiver side. So here, one of the works of Stefnak, their team has worked really a lot on the Volterra-based solution for visible light communication systems. They use a polynomial series expansion using Hammerstein, which is high computation complexity and delivers some modeling errors. Because you again have to, when you're modeling through Volterra, you have to stop somewhere. So I'll not go in detail, but basically there are issues, so we have to look for other solutions. So our approach has generally been based on RKHS-based one, reproducible kernel Hilbert space. This is another machine learning paradigms where we use kernel-based LMS or kernel-based MSCR type of that's minimum similar type of criteria to do adaptation. So this delivers a suboptimal performance over highly ISI channel, but otherwise it works very well. And then later we have explored. So we'll look at some of the other architectures of this thing in detail. Then Gazemloy, that's another very active group. Based out Northumbria University in Newcastle in the UK. They have used ANN DNN type of this to do non-convex computational things, and also looking at some algorithms for have a parameter free type of systems. So I'll say globally, if you look at so the Stefnak, Gazemloy, our group, and Professor Haas group. So these are four major three major groups that four major groups that are working on this. So Stefnak not with Gazemloy, our and then Pure Li-Fi are very active in this area. Then RKHS-based solutions. So we look at one of the solutions here as the time permits. And then because after this, we look at this newer form that we are looking at now, which is looking at the mobility aspect of the high speed mobility aspect of visible light communication system. So here, this is mostly either low speed or stationary type of system where there's not much relative motion between the transmitter and the receiver. Now, over the years, over more than half a decade, we found that RKHS-based posters are found to outperform classical polynomial series one due to several desirable features like complexity. It has lower complexity, universal approximation can be done, and low computational complexity. And also there is what we can do is analyze these systems. So as a researcher, I would like to know or have some kind of guarantees that this algorithm will work, or within certain range, this will work. However, that's not the case for other, some of the other techniques where the conventional feed-forward RKHS-based post sorters we have found to deliver suboptimal performance over multipath VLC channel impaired by high SI and non-Gaussian distortion. Now, hence, to mitigate this non-Gaussian distortion encountered in visible light due to severe ISI and user mobility, we have proposed recently a DFE, decision feedback based equalizer based post sorter in RKHS domain. So these DFEs, they have been known for many years, about 30-40 years they have been known. Yeah, I'll say just over 40 years, 50 years they have been known. But they have been known to have certain disadvantages, especially for non-Gaussian type of environment. So here we'll propose solution where you can improve the performance of a DFE based solution. Now, another motivation for us has been for about a decade or so is further the non-MMSC criteria like MSCR are found to be more stronger. So what is MSCR? MSCR is minimum symbol error rate or maximum Verso criteria. That's another recent thing that we have started to exploit and see if it works for our problems, and it works actually very well. And forms an alternative, I'll say, for MSCR and things. So again, if you have non-Gaussian distortion, which occur because of interference or other ambient other noises and all, so we need to look at some alternative. And as I'm designing a communication system I'm designing an equalizer. So my focus is on getting the getting the minimum bit error rate. Right. So here our focus is not minimizing a minimum mean square error type of criteria. So yes, it can in certain cases be mapped to that. That is perfectly fine. But then having a messy criteria is more stronger, especially when the situation is when the channel and the noise and the other factors that they are making the whole system to be a non-Gaussian distortions. And furthermore, RFF based explicit techniques are suggested which do not require specification. So this is something that we'll cover later. So our goal has been to develop new RHS-based adaptive signal processing algorithms for post distortion, basically equalization for VLC link under high ISA non-Gaussian techniques. Now let's look at the problem one. The problem one has been on LED nonlinearity. We want to fix the ill-conditioned massive MIMO channel, and there's a DC bias fluctuation. So the hybrid adaptive precoder and post distorter for massive MIMO is one of the solutions that we propose. So now to mitigate LED nonlinearity and reduce condition number of the overall channel matrix. So I want to reduce the condition number. So if you reduce the condition number, that means I'm going to get more of these independent channels, which is good for my overall performance. Now this conditioning process, we do it in joint RHS based MSCR pre-coding and post distortion by using this. So this, if you are interested, you can look into this publication in detail, where we propose a hybrid adaptive precoder and distorter. So here I'll touch base on it a little bit. So this is a typical example of a block diagram of a precoder and post distorter for a visible light communication. So basically I have a Capcom modulation scheme here. It goes through the precoder, that's a pre-distorter you can say. Then it goes through a DC offset. Then it goes to an LED array, which works as our antennas for transmission. Then we have a massive MIMO type of stuff. So this, like, you can think of it, let's say a tube light or a bulb using LEDs, so it can transmit. Then when it's put on the channel, so yeah, it has gone through this LED nonlinearity here, which is the function f. Then it is put onto the channel, then goes through the there's a relative wide Gaussian noise through because of the channel and the other factors in the devices. We receive it and the photodiode array at the receiver. It goes through inversion, then through a KMSCR based port. So that's our proposal here, which updates these weights, lambda k. So lambda k is updated here, and this information is then passed on to the precoder. So it is like you can think of it like a closed form, a closed loop of closed system, where the precoder and post distorter, they both are being adaptive. So this line, this dotted line, and this this arrow that is telling us that yes, some things going to vary here. So it is an adaptive filter. So it is learning as the system with the system as it goes. And this is a supervised learning based technique where there's some kind of training sequence which is sent before the information is sent. We have in the past worked on blind type of algorithms as well. That's also you can refer from the literature, some of our previous works, where there is no need to send this training information, but most commercial deployments require or use a training-based system. So here let's look at some of the system model as we define. So let xk, so that's a symbol vector. That's very small. So our notation would be a small alphabet, which is bold, refers to a vector. Capital will be matrix, and if it is not bold and it's not capital, then it is going to be a scalar. Now here, the input signal is multiplied by the precoder matrix P at the transmitter, and the received signal YK by the photodiode at the kth time instance is given by YK, which is a vector, is equal to H, which is the channel, times F P XK plus B. B is the DC bias required to put LED in forward bias, plus NK, the thermal noise, and the ambient noise. This can be generally modeled by, so the thermal noise can be modeled by generally by AWGN. So it's IIT process. We have it. So let's go into one of these in detail. So H is a massive MIMO matrix for NR receive times NT transmit. So here is LEDs and photodiodes. NT is the LEDs number and NR is the photodiode number. Then there's a thermal noise, it's modeled as IID AWGN. Then there's ambient light, it's modeled as a chi-square distribution, which tends to be Gaussian for large degrees of freedom. Hence, we assume it to be Gaussian, and sum of two Gaussians, we take it as a Gaussian. They both have zero means, so it just adds still a one bell unimodal type of distribution. And beta is the DC bias vector. So it has distortion, it has massive MIMO, it has nonlinearity, it also has DC bias distortion. And we use this type of model so as mathematicians or engineers, we like to have a model because we cannot experimentally do, not all of us can do experimental work on having a transmitter and receiver. So we have this very commonly referred model. It's a RAP nonlinearity model, which is given by this equation form. So f x tilde xk, xk is the, so that's the linear symbols that are coming in. So xk minus the V threshold. If xk is greater than VTH, then we use this equation. If xk is less than the threshold, then we take it as 0, where xk is equal to P times xk plus beta is the pre-coded signal, because there's a DC bias as well, and this has come through a pre-coder. That's why x tilde. Otherwise, I would have used, if there was no DC bias I'm considering and there was no pre-coder, then this xk will be the one that I'll put into the equation number 2. So x tilde k will replace xk if pre-coder was not there and there was no DC bias issue. Now here V max is the maximum saturation voltage. F x tilde is the output of the LED intensity. Then TH is the cutoff voltage of the LED, and Q controls the level of nonlinearity here. Right, so small q is the one that is in the numerator here. So 2q1, 1, 2q. Now the impulse response between then the complete impulse response between the jth LED and the ith photodiode is given by this expression. So already there in the literature, Hij is Ae p plus 1 divided by 2 pi d square ij cos p cos alpha cos beta, and then as well as a rectangular pulse of width t. So it is a gated type of signal. You can see a system that is considered. So alpha denotes angle of emergence with respect to the transmitter, again a massive MIMO system. Beta represents the angle of incidence, which is coming to the receiver. So this is the angle of emergence from this. So it cannot be a straight line. It might be at a certain angle from the transmitter. And P denotes the Lambert mode order, and alpha half is the transmitter semi-angle at half power. A denotes the effective collection area of the detector, and Dij denotes the distance between the ith and the jth LED and the photodiode. And phi is the field of view for the photo detector. Now there has been various contributions, so I will not go in all of them in detail, but basically what we have come up with a hybrid precoder and pre-pose starts using KMSA criteria. Another contribution is looking at the index using the precoder design to optimize as optimized using MSA criteria. Well, considering LED nonlinearity. So this is more closer to, I'll say, a practical system. An approximate expression for beta array. So theoretically, if I have all these issues and a non-ideal system, then what kind of beta rate I can expect? So theoretically we can do, and then we can find an upper bound on dictionary size. So they're usually based on so AICTE was taking that based on some kind of a dictionary we built in. So dictionary is storing some elements in your RAM memory. So that's where which is also a critical thing for a real-time system because we have a limited memory budget. And we want to see, okay, for that limited memory budget, if I put, let's say, 1,000 or 100 some coefficients in the dictionary. So if that is if I only have, let's say, memory of 100 elements that I can store, then what kind of beta rates I get? Because in theory, yes, you like to have infinite number, but then in practice, it is not feasible. So there is some kind of a trade-off. But we should know as engineers that what kind of rates we can data rates we can expect. So what we can do is maybe switch to another one. Yeah, or I can just go over this one first, and then yeah, maybe I just go through one of these techniques. So here, basically, what we do is look at the SVD of the channel. So we do a singular value decomposition. So you get these upper, lower, and the value matrix. So I get this left singular and right singular matrix, and then lambda is the diagonal matrix. Now a precoded the matrix is designed by this P is equal to V times lambda and that's lambda k minus 1, which is already given in literature, from where lambda k is between 0 and 1 is a precoding index in this. So this is something that we'll try to adapt. The lambda. Other things are not in our control. This is a system model, so they're not in our control. But here, if I do this kind of a decomposition of the channel, I can reduce my equation or write it in another form in equation number 5, where this combined at overall rep distortion can be considered as a so it could be a non-Gaussian process. It may not be completely Gaussian because I have these delta B is, so B is DC bias, which is a straight one type of voltage generally. Not, there might be fluctuations, but they may not exactly follow Gaussian thing. And then also for the channel as well, it may or may not follow a Gaussian type of scenario. So this overall adaptive distortion is there, which will denote by this. So if you look at this del is a uncorrelated distortion noise factor with zero mean, and covariance is this. So we consider this to be Gaussian, but it may not be. But mostly, in most cases, we'll take it as this. Again, to do theoretical analysis also becomes easier with this thing. So, and then delta B already I've given because it's going to be a DC. So it is a uniformly distributed minus epsilon and epsilon, a DC bias term. Then the effective channel matrix is given by delta U under this, and then we can take a ratio to find the condition number. Now the performance of precode is sensitive to the choice of lambda as observed from equation number 5. The smaller the value of lambda k reduces the condition number of active this and resulting in an increase in the peak to average power ratio of transfer. So it's not a good sign, so we need to have this lower. Hence, lambda k should be learned adaptively from the received signal. So I cannot fix it for all the conditions. So I have to adapt it based on my system model. And how do I do it? I do it in the AICTE space. I do a minimization of these two coefficients. Again, G is a MSCR constraint for QAM. So this we need to calculate for different type of modulation schemes. And then I can do a Lagrangian of this equation. I can expand it, take a derivative. I can find a gradient type of algorithm which is updating the lambda, because lambda is something that is sensitive. So gradient of Lagrange can be written as this equation number 9. Now the nonlinear problem in CN is converted to a linearly separable problem in RKHS, because in RKHS what we try to do is we move away from the nonlinear system, have these weights in the so apply a kernel on them, and after applying a kernel I can consider them to be linear, and I do all my operations in linear, and then come back to the apply kernel, and I come back to my original space. So that's why the RKHS techniques are very popular, and also because we can analyze them. So this kind of analysis generally is difficult for let's say you're using a deep learning or other type of algorithms. Because as you know, as engineers, we like to know, have certain bounds. We like to know if this my algorithm will converge or not, and to what kind of values it will converge to, or some range it can give me. So those kind of things that we need to look into. Now, if you look at the proposed post-distorter, because here we're looking at both pre and post-distorter. So post-distorter, we have these weights, lambda omega k plus 1, which is a vector, and omega k minus neta, again some factor, some constant factor, which we can again find a range for this problem. So this is quite similar to LMS type of equation, but here we have this phi, which is a kernel, and qk is another factor that comes in. So it is not exactly LMS, but it looks like a LMS type of expression. And we can find the recursive weight using this. So number 2 will be this, we call them 0, might be only zeros. So if I consider the first initialization of my weights to be 0, so all the values are 0. So omega 2 will be this factor, 3 will have 2 minus some factor, and then so on. So based on the mapped observation for KMSCR, I get this estimate of the symbol. So this is an estimate of the symbol, which is our ultimate goal. And because it's training based, so I can calculate the error. So this estimated one minus the actual symbol, I get an error. And based on that error, then I can use a MSCR criteria to do the updation. Now we need to do some kind of a sparsification, because we can use a dictionary, but putting all the symbols in dictionary is difficult. So we do some kind of sparsification based on certain criteria. It can be looking at the error or the distance between the two. If distance between the two entries is large, then we'll add it, otherwise we'll not. So there are certain criteria that can be used. Again, I'm not going to tell, but basically this is my algorithm for the updation of the weights. So this is what we covered. So we had this Q, which is defined by this for MSCI criteria. We check here if the symbols is there. So there's two of these conditions. If they are met, then we add it to dictionary, or we don't add it to the dictionary, and then it goes on iterating. Then you find the theoretical expression. We'll not go much in detail, but once we found this theoretical expression, we can then do an asymptotic BER, or try to find out what is the rate. We tested it on a typical system where we assume that the distance between the two neighboring LEDs is 5.8 centimeter, and the similar distance between the two neighboring photodiodes. An effective aperture area of 1 centimeter square, field of view 10 degrees, transmitter semi-angle 10 degrees. A distance between transmitter and receiver is 2 meters, and center of LED array, center of PD array, center for PD array. So given this kind of dimensions, so we were using this is 36, we're using 16 as well to see. And then we do run it over a number of iteration and see what kind of bit errors we achieve. So these are the first set of results for 16 cross 16 massive MIMO. S is 4 denotes a simulated dictionary, T denotes analytical upper bound on the dictionary size. So we use different dictionary sizes to see. So here for 16 cross 16, I mean, these are the bit error plots. So y-axis is bit error, x-axis is the SNR. So let's say at 100 SNR, I'm getting 100 dB SNR, I'm getting 10 to the power minus 5 bit error rate. So it is 1 bit in 10 to the power 5 symbols is getting into error, it's getting flipped. We have asymptotic bit array to n theoretical one. So just to validate if our analysis is correct or not. Then yeah, so we tried for different size of dictionary. We can go into detail in the paper. And similar behavior we see for 36 cross 36 as well. But here, if you look at it, so this is about 145 or 10 to the power minus 5, and here it was 100 into 100 dB. I'm getting to the power minus 5. So those changes in the curves will happen. But again, what we say is our theoretical analysis is valid for it's a generic equation, so it is valid for different number of transmit and receive antennas and different SNRs as well. It is a generic type of equation. So observations is that the proposed algorithm delivers about 10 dBs to 14 dBs gain from uncoded scenario. So which is quite huge, right? So for an IoT type of application, even 1 dB is a lot of energy, and here we are saving about 10 dBs energy if you use this algorithm. So um, again, it's good to use something rather than this no pre-coding or nothing to use. Okay, so I think what we'll do now is we'll switch over. So Anupama, are you there?
Yes, sir. Yes, I'm here.
Okay, Anupama. Okay, so what we'll do now, so these are mostly for static or low mobility type of systems. We'll give a small overview in the next 10-15 minutes. Just a small overview of different type of systems, and maybe look at one algorithm if possible on a system where we are expecting high mobility. Okay, so I'll skip this for now and stop sharing. How do I stop sharing? Share. Is it stop sharing already? No, I don't know.
It is still sharing.
Okay.
It is stopped, sir.
Stop now? Okay. Okay. Perfect. Okay. So, Anupama, yeah, you can maybe show
Okay, okay.
yeah.
Sure, sir. Sumit, is my screen visible?
Yes.
Okay. It's full screen now. Is it fine?
Yeah, it's fine. You can do.
Okay, just one more thing. Can you see it moving to another slide if I change the slides?
Yeah, it's
Yeah,
moved.
okay. Thanks a lot. Okay, good afternoon, everyone. I am Anfa Sharma, doing PhD under the supervision of Professor Vimal Bhatia. So these are the topics I would be covering as the presentation progresses. So now, as we have already learned that RF, it has been traditionally used as a medium for communication since a very long time. But now, uh, because it is congested and there are a lot of issues with RF, that there is electromagnetic interference, and because of that, we cannot use it in places like hospitals or airplanes. So now it is necessary to look for other mediums which can cater to the need of increasing users without compromising with the data rates. And in this context, VLC has demonstrated itself as one of the viable solutions. But as we have also learned in the presentation by sir before, that the performance of a VLC link, it deteriorates due to mobile receivers, and because of the multi-parts between receiver and transmitters, the LEDs in the user of our mobile phones, which causes delay in the Doppler shifts. The delay shifts which are caused due to the time dispersion because of the multi-paths or the mobility, it leads to inter-symbol interference. And the Doppler shifts, they causes inter-carrier interference. Now, to mitigate the ISI, there are many conventional schemes which are already proposed for VLC, such as optical orthogonal frequency division multiplexing. I mean, they are already proposed and they work well for a less complex system. I mean, for a static system where the multipaths are not much, but as the multipaths increases or the other complexities are introduced into the system, for example, the user mobility, the OFDM, it fails. I mean, it does not fail, but its performance reduces and the receiver complexity increases to get the same performance. So To mitigate both ISI and ICI, recently low complexity generalized orthogonal time frequency space modulation scheme has been proposed. Wait. Let us consider this scenario. It's an outdoor scenario. So we have this is our transmitter, and these are, for example, let's say buildings which will from which our light would be reflected. And we have considered two users. One is a static user, this person, and another is a mobile user. So they would be getting data from a line of sight path, or after getting reflected from the buildings, from various buildings, trees, or there might be many reflectors. There are many reflectors in the environment. So, considering for this static user, the delay from the line of sight path would be d1 by c. C is the speed of light. D1 is the distance between this transmitter and the user. The delay of the reflected part would be d2 plus g3. This is the total path traveled by this particular ray. And the delay spread for this person would be tau1 minus tau2. Tau1 was this delay, and tau2 was the delay of the reflected path. And considering for this car, for example, let's say it is moving with a velocity v towards the transmitter. So their relative speed would be not, the transmitter is static, it's not moving. So their relative speed would be v. So the Doppler shift for this line of sight path would be fc v by c. And for this reflected path, it would be fc v cos theta by c. V cos theta is the velocity of the car in the direction of this ray, the direction of the data it is getting. And the Doppler spread for this would be this v2 nu2 minus nu1. So before moving on to the OTFS, we need to understand the drawbacks of OFDM. So in OFDM, it mitigates the effect of ISI and ICI in a static system or in a less complex system, but the receiver complexity, it increased tremendously if we include user mobility or the multipaths. And if the user is mobile, Doppler shifts can destroy the orthogonality among the subcarriers. This results in ISI, which degrades the performance. Also, WebDM does not account for the Doppler shifts, which we'll see in the next slide, and introduced due to the receiver mobility, causing channel time variation. And also, there is no inherent channel sparsity, which causes suboptimal performance even in the static system. We will show this from our results as well, that even if our system is static, OTFS performs better than OFDM because there is inherent channel sparsity. So in the case of OFDM, our channel impulse response, we write it as h tau is equal to summation I is equal to 1 to Cp. Cp is the number of paths, hi delta tau minus tau I. There is no this term is not there, delta nu minus nu I, which is because of the Doppler shifts. So considering the same example here for this car, so okay, so let's say it's getting information from three paths. So one would be the line of sight path. This is noted by this black dot. The size of this is bigger because it's getting maximum power from the line of sight one. So there would be no delay, and there would be some Doppler because this is moving. It may be getting some other data from, let's say, from this path, and there would be some delay now and some Doppler as well. So this is how we place our channel coefficients in the case of an OTFS system. So this is how it is equated as given in equation 1. So this is a literature review of what has been done till now in OTFS. So OTFS advance was proposed by investigators in paper 1, where they have shown that it performed better than the traditional OFDM technique in terms of both packet error rate and the bit error rate. And an extensive investigation on the performance of OTFS and OFDM is done over static multipath channels in RF only by investigators in paper 2. Next, the complete error performance and diversity analysis of OTFS modulation is also done in doubly dispersive channel. There they have considered the mobility as well, without assuming any bi-orthogonality assumption by authors in paper 3. Next, I mean, if the our waveform is ideal, there is no interference in OTFS also. But if we consider practical waveforms, like in rectangular or sync pulse, then the interference comes into the picture, and for that as well, OTFS performs better than OFDM. This is shown in paper 4. Then for besides RF, OTFS has been implemented in millimeter wave communication and in the acoustic water communication as well, where it has performed better than the its counterpart, the OFDM. So this is the system model. So we have considered, I mean, for the results we will show later. So we have the data bits which are form modulated. Then there is this block where we do the OTFS modulation. Then some DC offset is added to bring our data in the forward bias region for LED to operate. Then with the help of LED, we transmit it through a VLC channel. Then some noise is added in the process, and the data it is finally detected at the receiver. Then we do the OTFS demodulation. Then detection is done, and we do the demodulation, and we get the detected symbols. So let's say that number of symbols that are transmitted per frame is ns, which is equal to kl, where k is the number of symbols and l is the number of subcarriers, respectively. The transmitted form symbols is denoted as this small s, and the OTFS modulation is performed on s, and cyclic prefix of length Cp-1, where Cp I have told for it is the number of parts, is appended to the result of the OTFS modulation, and then we add DC offset, and the same the inverse of this is done at the receiver. So OTFS modulation, it can be done in 2 steps. I mean, it can be done directly using a ZEC transform. But ZEC transform is a little complex to do, so we do it in 2 steps. First, we do the ISFFT transform, and then we do the Heisenberg transform. So our data, which is mapped in delayed Doppler domain, it is brought into the time frequency domain using this ISFFT transform, and then we perform Heisenberg transform on this to bring it to time domain for the purpose of transmission. Then at the receiver, the inverse of this is done. We do OTFS demodulation, which can be done in 1 step using inverse ZEC transform. But again, it is done simply in 2 steps, which are Wigner transform and then SFFT transform. So the data which we are getting, which is received by the photodiode, is in time domain. We need to bring it to the time frequency domain first, and which is done by Wigner transform. And this time frequency data is then brought to our information domain, which is the delayed Doppler domain, using the SFFT transform. So this is a simple system model for OTFS VLC system. Coming on to the channel models we have considered. So we have considered actually 3 types of channels. The first one is IEEE PAN 802.15 VLC channel model for VLC. It's the static one. Next is the time varying channel model for VLC, and then the random wave point channel model. Coming on to the IEEE PAN 802.15 VLC channel model, in this we have considered 3 cases, 3 environments actually. The first one is home, then open office, and then open office with cubicles environment. So for the home environment, the RMS delay spread is 9.24 nanoseconds. In open office environment, it increases to 15.27 nanoseconds. And then in open office with cubicles environment, the RMS delay spread is 12.68 nanoseconds. So next is the time varying channel model for VLC. So this picture is actually of the from the top view, where these 9 yellow circles, they are the luminaries. These 3 lines, blue, red, and the black one, these are the trajectories of the users, and these black dots, they are basically the start point of the user. So yes. So in this model, the path loss function, we find the path loss function, and we have plotted the path loss for the 3 trajectories. It is given by equation 3, where these KLJ, LJ, and MJ, they are the coefficients given in this table too. So these are the path loss versus distance curve for the 3 trajectories, and we have used this model later. I will explain in the results, but these trajectories means. Next is the random waypoint channel model. For this model, the probability distribution function is given by equation 5, where these coefficients pi's and alphis are calculated as given here. And the h is the channel coefficient. It lies between some minimum and maximum value, h min and h max. It can be calculated. It is given here and can be referred from various papers as well. So now using the above channel models, we transmit our information symbols through the LEDs after adding the cyclic prefix. And at the receivers, we first discard the cyclic prefix after receiving our data from the photodiode, and the transmitted symbols and in time domain and the received symbols, the relation between them can be given by equation 7, where this h tilde is it's a circulant matrix given by 7. Then, as I have mentioned this already before, the CIR, the channel impulse response in the information domain, is given by equation 8, where these mu I, tau I, and HIs, they are the Doppler shift delay and the channel gain for the ith cluster. Now, at the transmitter, first our symbols, they are mapped in delay Doppler domain, and they are brought to time domain using these two steps, which are given by equation 9 and 10 respectively, where this Gx is the transmitted pulse. So if this transmitted pulse is ideal, there is no interference. But if if it is practical, then it causes some interference, which can be easily mitigated. Next, at the receiver, we receive the signal, which is given by equation 11, and it is then again brought back to the information domain, which is the delay Doppler one, using these two steps, which are it is given by equation 12. And this SXC is the received pulse. So in the time frequency domain, the input output relation is given by equation 30, where the H&M in time frequency domain can be derived from the channel in the delay Doppler domain using equation 14. And then after we have done the demodulation, the OTFS demodulation, now we need to estimate our symbols and detect them, which is which can be used using detector, message passing detector. So in lots of paper, in lots of the literature, if you go through the literature of OTFS, you will see that the detection is done using this message passing algorithm, because as I mentioned before, that there is inherent channel sparsity in the case of OTFS. So message passing algorithm, it takes advantage of that. So this is the algorithm. So what we put in input as the signal vector received in the effective channel matrix. Then we initialize our probability mass function as 1 upon this symbol A, which is the which are our alphabets basically. So if for example we are using BPSK, our alphabets would be 1 or -1. Then Imix is the maximum iteration for maximum number of times we are going to run. Then for computation, we first compute the mean and the variances of the interference plus the noise terms that we have received at the receiver. And we pass in through observation nodes to variable nodes as the messages. Then the variable node, it updates the probability mass function using the message received, and then it passes to the observation node. Based on that, the decision on the information symbol is transmitted. And then we increment I and repeat the process till I mix. And then we receive our detected signal vector S head. So coming on to the simulation results. For this, we have considered the number of symbols transmitted per frame to be 1024, and the number of subcarriers are 128. The modulation alphabets we have considered are BPSK, binary phase shift keying, and the QAM. quadrature amplitude modulation. The size of the room is 6 cross 6 cross 3 meters, and the LED half angle is 40 degrees. The optical power of each luminary is 11 watts. The field of view is 85 degrees, and the area of detector is 1 centimeter square. And the radius of the maximum coverage area of the LED is 3.15 meters. So this is the BR performance of OTFS and OFDM for the home environment, which is from the IEEE 802.15 channel models. So it can be observed from this figure that that OTFS delivers a gain of 6 to 7 dBs at bit error rate of 10⁻⁴ for both 16 QAM and 32 QAM, is because in OTFS all the symbols they are expressing the uniform channel gain. Similar results are observed for the open office environment. In this as well, we saw that the OTFS delivered a gain of 6 to 7 dB at BR of 10⁻⁴ for 16 and 32 QAM. Next is the open office with cubicles environment. So we see the consistency that as we are changing the environments, the OTFS it is giving us a gain of 6 to 7 dB in comparison to OFDM, which is actually very huge. For a bit error rate of 10⁻⁴. So the accuracy is also maintained. Next is for BR performance of OTFS OFDM for the time varying channel model 1. So in this we have actually calculated the threshold value. I mean, we first saw where the path loss is maximum, and then we are calculating the threshold SNR, for which we will get a bit error rate of let's say 10⁻⁴, because in this particular case, we are actually fixing the position of the user, and we are trying to find we are placing our user at the worst possible position in a room, and we are trying to find the threshold SNR, which will give us a bit error rate of 10⁻⁴. So using both OTFS and OFDM here, we see that for 4 QAM, it gave us a gain of 7.25 dBs. And for 8 QAM, the gain observed is 6.65 dBs by using OTFS. And then for 16 QAM, OTFS it delivered a gain of 8 dBs over OFDM. So we are getting an advantage of 6 to 8 dBs in this particular case as well to get a BR of 10⁻⁴. Next is this for random waypoint channel model. So here the mobility is also involved. The user is moving using a random wave path, and in this we observe that OTFS delivered a gain of 9 to 10 dBs at bit error rate of 10⁻³ for both BPSK and the 4 QAM. So with this, we can actually conclude that in time varying channel model and the static ones as well, OTFS with message passing detector performed better than the OFDM. With in OFDM we use the minimum mean square error detector by 6 to 8 dBs. Then for the random waypoint channel model, the OTFS performed better than the OFDM by 9 to 10 dBs. And from this we can say that, and from the applications we have already seen this, that LED is the visible light communication is already being deployed, and people are actually putting them in place and trying to see how they are performing. So it's a promising solution for practical deployment of VLC systems for beyond 5G based communication system, and for operation under dynamic channel conditions. For example, in vehicle to vehicle, vehicle to infrastructure communication system, where the channel adaptation is complex. The channel is changing at a very fast rate, we can say. Then LEDs, they have now for the future work, as we have already seen that LEDs, they have non-linear characteristics, and that that includes that induce mitigations because of the non-linearity. So we need to include this in this system model as well. Also, because of the reflections, the LED, the light rays, they loses power every time they reach the user. So there are schemes coming up for that as well. So that needs to be explored as well. So these are the references. Thank you. If there are any
Anupama.
questions, yeah.
Participants, now floor is open for the questions. You can unmute yourself and directly ask your question to the speaker. Any question from participants? Okay. I think there are no questions from the participants. So let's thank our speaker. Thank you, Anupama,
Thank
for
you.
such a wonderful talk. And thank you, Professor Bimal Bhatia, also for sharing your so valuable time and effort. You took so much effort to share your experience with us. Thank you, sir. Now, I request all the participants if you can please switch on your videos so that we can take a screenshot. Participants, please switch on your videos. Participants, please switch on your videos so we can take a screenshot. Okay. Okay. You can. Thank you, sir. Thank you, Professor Bimal Bhatia, sir. You can.
Thank you.
Switch on. Thank you, sir. Okay, so we will be taking a lunch break. So we will meet for at 3 p.m. for the next lecture. Uh, for now, we are taking the lunch break. You can have a and we'll meet at 3 p.m. Thank you. Good afternoon, everyone. Now, I welcome you all in the third session of day 4, which will be delivered by Kumari Jyoti. on RM in medical image processing and in-memory computation. Kumari Jyoti is a research scholar in HNRG lab. Now I would like to invite Kumari Jyoti to share her slides and continue with the lecture.
Thank you, Sumit. And before I start my presentation, I would like to give a special thanks to my supervisor, Professor Shaibal Mukherjee sir, for giving me such wonderful opportunity to present my work at this platform. Thank you, sir. So, Miss, please let me know that whether my screen is visible or not. I'm just sharing it. Is my screen visible?
It's visible. Please continue.
Okay. So, today's session is on RM based on medical image processing. Basically, we used initially Lina image also for the processing and some other images like APJ Abdul Kalam sir and Gandhi ji for the initial understanding of the processing and how in-memory computation is going on. Because our objective to implement that memristor crossbar array in that image processing areas. So in today's session, we will see basically what the motivation we have toward using that RM in image processing specifically. And then we will see that how this memristor based analytical model is used for compressing our images. And then we will see there are so many different techniques for decomposition like DCT, Fourier transform, discrete cosine transform, discrete wavelet transform. So why we are going toward discrete wavelet transform instead of discrete cosine transform and others technique. And we'll see the MATLAB programming also with its simulation result step by step so that you can may understand clearly that how's the process going on. And we'll also implement this model on CNN, convolutional neural network. And the heart of that convolutional neural network is activation function. As if some of you, if worked in CNN or ANN, so you know the importance of activation function. So we'll replace that sigmoid or 10H activation function by our window function, which is designed in analytical modeling process, which is already discussed in our earlier sessions by sir. So we will see that part also, that how we implement our model over activation function and how we can recognize our pattern of digits, that is 100 or 001, much accurate compared to already inbuilt function of sigmoid or hyperbolic tangent, ReLU function, activation function are there. So everyone having their own specification with some advantage or some disadvantage also there, which is removed by RM models. After that, we will see other decomposition technique, which we are working with, that is tunable Q wavelet transform. Here Q stands for quality factor. So basically in this, one more extra study we will do that is not, we can cover in 2D discrete wavelet transform, that is oscillatory behavior of the signal or image we can say. After that, we will see the memristor system in convolutional neural network, how it works and what the work we are going to do in terms of facial recognition. We are trying to use that memristor crossbar for recognizing face so that data safety and security. See, right now also in many factories and companies, they're using some detection technique of face for attendance purpose in colleges or institute. Now, in most of the colleges or school, our faculty member or teachers using attendance by calling their name or roll number. But in some institute organization, they're using some detector there by where you go and by detecting your face, they can mark you as a present or absent. So this kind of facial recognition also happened by using memristor crossbar system stack wise instead of CMOS based circuit, because the effective storage of memory, or we can say efficient storage of memory with the less power consumption, we will see how we use for storing this facial recognition application. Then at the end, we will see what the conclusion overall of this session, and references is mentioned in every slide at the bottom. So initially we try to cover the portion that what's the motivation actually we have for using this RM resistive, that's full form. I hope everyone knows that resistive random access memory. So basically here we have resistance with memory, means here we have memory is the combination of two words. A memristor is the combination of two words, that memory plus resistor. That resistor which behaves as a memory. How it possible? Basically, resistor is the function of, or we can say it's a ratio of voltage with current. So voltage defined as the rate of change of flux with respect to time, and current defined as rate of change of charge with respect to time. So basically, resistance only store the present point of time values or data. But in case of memristor, we will store the previous state also. In earlier session, our senior sir already mentioned that what's the set process, what the reset process. So basically, this resistant states decides the what storage of data will happen in that device. So firstly, the memristor having higher density to store data, and it is non-volatile, and its speed is much more higher with less consumption of power, or we can say energy. Its writing time is very faster compared to ongoing CMOS technology, and it is a great reliability. When power is interrupted also, then also it get not that much affected. What the effect we will observe in CMOS based circuit or FPGA based circuits. Here we can see a basic difference here between transistor and memristor device, that transistor is 3-terminal device, whereas memristor is 2-terminal device. Here we have top electrode and bottom electrode where we're giving supply. So basically, memristor device depends on the resistant state, whether it is set or reset. What set? When we go from higher resistant state to lower resistant state, then this is called set process. And when we go from lower resistant state, or we can say high conductance state to low conductance state, so this is called reset process. Similarly, here in transistor, we can say that this electron charge is basically responsible for storing the data, and that electron charge depends on power supply only. So that, as in second point already mentioned, that it requires power source for storing this data. But in case of memristor device, does not require power source to retain the data state. When the power supply off, still the data will remain stored in this memristor device. Last point is I mentioned here that transistor capable for performing analog or digital function depending on the applied biased voltage. For digital, we are giving 0 volt or plus 5 volt. But in case of memristor system, if you want to perform analog function or digital function, so it depends on particular material selection. That at initial stage in 2008, Williams used like titanium oxide. In our lab, our super seniors use zinc oxide as a resistive switching material. One more super senior is there. He used yttria oxide, Y2O3 based material resistive switching. So basically, material to material, our cost is also vary, and the performing parameters like endurance, retention, resistance ratio, these parameters which will decide the effectiveness of that memristor device or memristor crossbar will vary. So this point we will see more in our coming slides. In other part, we will see that this artificial brain, basically we try to replicate this artificial brain by this memristor crossbar. Here we have top electrode, bottom electrode. Well, as we can see in this part, that 2 pre-neurons and 2 post-neurons we have. So basically, we have in memristor crossbar array already you all have seen in earlier session that we have top electrodes and bottom electrodes here, which will work as a pre-neurons and post-neurons. And between these 2 electrodes, we have resistive switching material which works as a synapse for neuromorphic computations. And here we can see that the medical applications, in many applications we can use, or we can replace the CMOS based technology, transistor based, and we can say ASIC, that is application specified integrated circuit, we can replace for efficient storage of data with the lesser power consumption, or the complexity of the solving the problem is also easier in case of memristor compared to CMOS or FPGA based technology. So in our work, we used medical applications by taking the images of CT scan or MRI, including some data set, large data set and a small data set of COVID-19 images of chest X-ray we considering, and we get very good results compared to all those techniques which going on in the market by using CMOS technology. So another work we can also perform, that is phase detection, and how it will get performed we'll discuss in coming slides. Biometric operation we also use in biometric operations this memristive crossbar array, and in the radar system or satellite communication, for let us suppose we want to check what's action of human activity going at the India-Pakistan border. So we can use memristive based chips instead of CMOS or transistor or FPGA based circuit, or in short we can say application specified integrated circuit nowadays use everywhere, where mostly we use CMOS circuit, but we have much more benefits of using memristor in place of CMOS. We will discuss that points in coming slide, that what points there we have in which we can prove that memristor is much better than CMOS, and in coming scenario we will replace that CMOS based circuits by memristor in that satellite communication as well as in radar communication also. We can use that in object recognition and signature verifications also. So these all are the part of image processing basically. In case of if we terms for the comparing of the results, so we can discuss in such a way that in case of power consumption, if we compare CMOS with the memristor based circuit, so here one paper reports the value that CMOS based full adder circuit will consume 117.3 microwatt, whereas memristor consume power 53.08 microwatt, which perform better, means give better results and also consume lesser power. Similarly, in terms of number of transistors, basically in nowadays complete memristor based circuit is not in market, so some 1T1 or combination is used in place of memristor. So some transistor also used for the same operations, which is performed by CMOS based full adder circuit. So in CMOS based full adder circuit, 34 transistor is going to use, but in case of memristor based full adder circuit, we use 24 transistors. So the area consumption is also reduced, as we can see by the using number of transistors lesser in memristor based full adder circuit. And if we talk in terms of processing speed, so delay happens in CMOS based circuit will be 75.3 picosecond, but in case of memristor it will be 62.4 picosecond. So these are the one points. Another, if we talk in terms of a number of operations like multiply or add operations is going to happen there. So how much one memristic crossbar array is there, where we trying to store, means in this paper of Halwani, they try to store compressed image of Lina image, that's resolution having 128 cross 128. So when they try to conventionally store that image, so by using CMOS based circuit, so they try to do multiplication and addition operation 4 cross 5 times, means with that per pixel image we multiplying and adding operation by 20 times. But once we use memristor for storing this 128 cross 128 Lina compressed Lina image, so we just applying 2 cycle of operations for multiplying and addition. So in this case, we will see here that 10 times of number of operation reduction we observed in memristor based computing compared to conventional digital based computing. Another thing we will see in terms of area consumption. So in case of memristor based computing, what we observe here that the area consumption in memristor based computing is 7,864.2 micrometer square. But in case of conventional digital based computing, where CMOS based circuit is there, so they try to store that data by consuming the value of 0.3270 millimeter square. So here again we saving 5 order of magnitude area when we go for memristor based computing. Another processing speed we observe here that by CMOS circuit processing happens of that storage process is 19.2 microsecond, but in case of memristor it is 15 microsecond. So again, this is not very higher data, but we can increase this data because day by day there are so many excellent work is going on by changing the materials of the top electrode, bottom electrode, as well as resistive switching material. So we're getting much higher, better performance compared to already published data. So obviously this processing speed right now, the saving 1.28 times, but we can increase that processing speed also in coming days. And the total, if we talked about in terms of total energy, so in conventional digital based computing, the total energy they consume is 70.908 nanojoule, but in terms of memristor based computing, they use 6.4398 nanojoule. So here again we can observe that memristor based circuit saving 11 times power consumption compared to conventional digital based computing. So these are the motivation toward work toward image processing in, with the platform of memristor, because it is very efficient storage of data. Now, if we talk in terms of digital image processing, that's why we want to go in this area. So most of the work nowadays going on a digital platform, and as we can see, that the pictorial information is very much important for human interpretation. If you want to understand anything, or most of the works is going on in pictorial form, so we need to transfer this data efficiently with the less time consumption and with the efficient storage, as well as less amount of area consumption will be there, and it should be simple in processing work. So this is our motivation to work for image processing basically. And then one more point we can say that autonomous machine perception is also going on in there, where we need to store and then transfer that data as per according to requirement. If you go in terms of IoT platforms, or we can say artificial intelligence, so there we also use this digital image processing in silicon brain computing. So in this figure 1, I just took a image block diagram of image compression and decompression technique, in which we will see that how this complete process is basically going on. Initially, we have taken some original images. Let us suppose I am taking Lina image or some medical images like CT scan or MRI of some want to diagnose some whether that person having COVID-19 or not. So initially, let us suppose I'm just considering that original image as per its resolution. Mostly we use 512 cross 512, means 512 cross 512 resolution, or the size of that image, which is going for forward transformation. And forward transformation called basically there are so many transformations which we can say comes under this list. Forward transformation, we can consider Fourier transform, we can consider discrete cosine transform, we can consider discrete wavelet transform, we can consider tunable qualitative wavelet transform. So on, as per according to our application part, we go for a different kind of transformation. In our case, we need to compress our image with enhanced quality of image. Basically, this enhancement in the quality of image we will get by using discrete wavelet transform. In case of discrete cosine transform, we are not getting that much higher PSNR, as well as we have much more complexity also compared to discrete wavelet transform. So here for forward transform, we using discrete wavelet transform. Once we did this, so the quantization process is going on. Let us suppose if I'm using memristor and I want to quantize it in between 0 to 1, or some quantization for the particular values, if you want to consider it, because we are just removing the redundant data. So now out of 0 to 1, if we consider from 0.5 to 1 data, should consider as one value, we mark it as 1, and from 0 to 0.5 we want to quantize it at 0 value, so we consider those values are as a 0 value. But memristor having one benefit that they can store value in between 0 to 1. So how we utilize that benefits also we'll see in coding part. After that, we will code all those coefficient whatever we are getting or receiving after that compression part. from forward transformation step. So we collect all those wavelet coefficients in coding part, and then we pass through our model, or we can say this coding data we can transfer also from transmission channel, and at the receiving end we again decode those data, dequantize in the reverse way. Let us suppose if we quantize that values in some particular way to 0 to 1, so we at the time of dequantization we just reverse that process. And in inverse transform, let us suppose I am using discrete wavelet transform. So at the inverse process, we are just synthesizing that data. At the end of receiver, we synthesize data, and at the end of transmitter, we analyze that data. And at the end, we reconstructed our original image by doing all this inverse process at the receiver end. So this is basically a complete image compression and decompression block diagram. If we go for further relate that image compression part with the memristor crossbar, so basically we have that memristor crossbar, let us suppose of 512 cross 512. So we have we can use that memristor crossbar as a vector matrix multiplication. There we can store the digital images by giving that voltage supply pulse. Let us suppose I have image. After compression, we can reduce, obviously. Let us suppose I'm compressing that image from 512 cross 512 resolution to 64 cross 64. So that I can store that image in memristor crossbar of 64 cross 64, and per pixel having some intensity of that particular image of that particular pixel. So I just store that image in that particular location of that crossbar. Let us suppose I have 64 cross 64 crossbar size, means we have rows and column of 64 numbers. In first pixel, I store the first part of that pixel point, and we'll see that part clearly in the diagram of the image MATLAB coding as well as in simulation result. We'll see clearly that how we can store all those pixels value there. After that, we'll see this analytical model already discussed in earlier session, that what the importance of it and how this results already designed from the experimental result of yttrium oxide. So this part is already covered. We will go for the flow of work, what we are using in image processing simulation part. Initially, we are just calling the image. If I'm just considering one image of APJ Kalam, sir. So we are calling that input image, and we just generate zero matrix a bitmap for storing those images pixels value. So for storing that pixels value, we need to generate one zero matrix there, and once that matrix is generated, so we convert that input image pixels value into voltage matrix form. And then we convert that voltage matrix form into the input voltages. Let us consider I have a grayscale image. So grayscale image having a range from 0 to 255, because per pixel having 8-bit storage. So I have the scale of 0 to 255, and I want to store complete value in this matrix voltage matrix form. But there we have one advantage, that we can store that value in the range of 0 to 1 also. So we need to scale that value or normalize that value from 0 to 255 scale to 0 to 1 by dividing that value to the maximum of that range. In case of color image, we have 3 plane, which we will see that RGB, and in that case number of samples going to increase, and accordingly our voltage matrix going to increase. In case of binary, the voltage matrix is of same number of pixels we need to design, but in case of gray, for per pixels we need to design voltage matrix in terms that 8-bit should be stored there, and if not, then you have to normalize that value between 0 to 1. After that, we will see that that converted voltage matrix into input voltage by that current voltage relation, what we already discussed in analytical model part, that we have some relation between input and output current, or output current by input voltage. So once we giving supply of input voltage with some constant parameters are there, which depends on experimental fitting parameters. So A1, B1, A2, B2, our values are already defined there, and we use this V1 in sine hyperbolic function. So we can calculate the output current, and once the output current is calculated, so by using that V of I and output current, we calculate this memristance value, and we generate the matrix for this both current and voltage memristance also, and then we again calculate the output voltage by using this M of T and output current values. And once we get calculated all those output voltages, then we design output image by considering this output voltage as a pixels value of that reconstructed output image. So at the initial stage, we use these three different grayscale coding. One is binary, another is in gray, and third one is colored. In case of binary, we using resolution of 1080 cross 1080. In case of grayscale, we assign per bit as 8 bit. So we are seeing here resolution of 1125 cross 15,000, but per pixel also having a range from 0 to 255, or we can say one pixel having a range, or we can store different values from 0 to 255. So in that way, the number of samples in case of grayscale is higher compared to number of samples in binary. And if we talked about in terms of colored image, where we use this main gate pictures of Iot Indore. So in this, we having resolution of this image is 4000 cross 3000. And in color image, we having 3 planes for defining that colored image. That is red, blue, green, RGB plane we said. So one plane having the same level of range for representing that bit, that is from 0 to 255. So here we have 3 cross 0 to 2556 range, and that we can say the number of sample in colored image is much higher compared to grayscale, or we can say 3 times higher compared to grayscale number of images. And then binary is having more number of sample compared to gray having more number of sample compared to binary images. And in case of assessment parameters, we can study that these values we observed here. And what the importance of these values? That peak signal to noise ratio gives the quality of the image, how much clear it is, and how we can relate that whether the binary image having the higher peak signal to noise ratio compared to gray or not. And if yes, it is that binary having higher peak signal to noise ratio compared to grayscale, or grayscale having higher peak signal to noise ratio compared to colored image, then what the reason behind it? If we getting error higher in case of colored image compared to gray, and getting higher error in case of gray images compared to binary, then what's the reason behind it? So all the reason depends on the number of sample, that how much number of sample we having in colored image and how much number of sample we having in gray or binary images. If we go to think in such a way, so we come to know that color image having more number of samples. So if we having more number of samples, so the chances for getting error is higher in case of colored image compared to binary and gray. Here also we can see in gray images, the error is higher compared to binary images. The similar study we have done for standardized images, because those previous pictures are not reported in some papers, but these grayscale images and Lina based basically grayscale images or colored images in most of the research people's use. So at the initial work, we use these images for calculating how much PSNR or mean square error we can calculate by using that memory strip crossbar array, or the analytical model, which is basically designed from that ATAL oxide based experimental result. So here we come to know that by using that PSNR values, that we are getting little lesser compared to what the already reported result are there. And in case of colored image, we are getting higher value when we using resolution lesser with the less number of memory size. As we increase the memory size from 15 to 40 KB with the same resolution, so the again the quality of the image in terms of PSNR, we observe that it get degraded. And in color image, for the same image, if we increase the resolution also, So again, the number of, or we can say the quality of the image get deteriorated, or the value of PSNR get degraded. So we can simply say that as we go for higher number of samples for the same image, so the error going to increase and the PSNR value going to decrease. In some paper, people use discrete wavelet transform, or we can say other forward transform techniques for storing those images in basically in our memristive system, memristive crossbar system. So they try to use instead of direct that input voltage, as what I mentioned already, that we considering one image and considering its pixels value as a voltage input in our analytical memristive model. So instead of that, they're trying to use some discrete wavelet transform where we getting some higher PSNR compared to without using any forward transform is used to store that image through our memristive model. In compared to that, if we use and we go for discrete wavelet transform, so the storage is much more efficient, and the memristive model can directly take this coefficients value, what we are getting by applying this two-dimensional discrete wavelet transform. So in this slide, I just want to mention that what's the basically internal diagram of that discrete wavelet transform is going there. Because in MATLAB command, we just use 2DWT, and backend processes that much already happened. There's no need to go for all low pass filter and high pass filter for each level. This is already inbuilt in MATLAB, but you have to understand that what's actually discrete wavelet transform is going to do here. Initially, we are taking Lena image, and we apply low pass filter and high pass filter through its rows. So what happened, that low frequency component collected at the upper side, and we getting that complete Lena image is divided into half portion. That is, the complete image will be seen at upper half, and the high frequency component, that is called details component, will be seen at lower part. Once we applying this over the rows column, once we go for columns operation, then again we apply that low pass filter and high pass filter throughout that column. So we getting again that low frequency component is getting selected at one region, and the high frequency component is get selected at the other region. So we mention it as LL, that will tell us that low frequencies are applied over the rows of that complete image, as well as low pass filter is applied on the columns also. So from here, we're getting complete low frequency component. And as we already studied in our basics of engineering or MTech, that we having some Gaussian pulse where we try to observe, or we can directly confirm that the low frequency component having much more information compared to all high frequency component. And at the end, we try to assume that okay, 5% if redundant data, or we can say some information may loss. But if we just store that low frequency component, so we can cover 95% of actual information what we try to deliver from transmitter and to receiver end. So the same concept is also applying here, that we just try to take those coefficients which having some useful information, and the details coefficient like low pass filter applied over the rows and the high pass filter applied over the column, and we getting LH coefficients, which is horizontal details coefficient. So we consider this as a details coefficient, and we can remove this coefficient at the time of transmission whenever we didn't get that much loss, and we may feel much more efficient storage of that image, as well as less consumption of that bandwidth. Also, in terms of area, we can say lesser area may consume by compressing that image in terms of LL. Similarly, for another image, that is high pass filter is applying over the rows, and then low pass filter applying over the column. So we get details coefficient vertical, that is HL, vertical details coefficient. This is also redundant data for us, and we are not using that for further transmitting of the images from one place to another place. And this HS called high pass filter is applied over the row as well as column, and this is called as diagonal details coefficient, which is also one of the redundant data. And there we can see for when both the high coefficients is coming, so the quality of the image is degraded, like very much higher compared to other 2D details images, because they're still having some low frequency component, but in case of HH there is no any low frequency component, and this quality of image is literally very poor as compared to other three. But at the end we use only LL or approximation coefficient value for further decomposition or for further transmission of data or image from one device to another device. So what's the basically the process of decomposition and reconstruction is going on? We'll see in this slide that initially I have considering Lina image. Basically this operation is also done for medical images also, that is already reported under review in IEEE transaction journal. So we cannot directly show all those results or data which is already is under review. So I'm just taking the same operations with another image, that is Lina image here. So input image, Lina image, considering of resolution 512 cross 512, we go for discrete wavelength transform. And at the first level decomposition, we come to know that this 512 cross 512 decomposes into 256 cross 256 each block. And as I mentioned in previous slide, that we need to focus on low frequency component instead of all details coefficient, that is HL, LH or HH. One represents that this is a first level decomposition. The same operation of discrete wavelet transform is applying next time on only LL component, that is approximation coefficient. Once we apply this discrete wavelet transform second time over that LL1 portion, so we get again 4 different subbands there. Like here we can say that LL1 having resolution of 256 cross 256. So again when I decompose it by half, then I'm getting 128 cross 128 resolution of LL2 image, and this is basically we try to use for further decomposition or for further transmission. Or if I'm using some medical image here, so for diagnosis purpose also I try to use that LL2 portion. In second level decomposition, we representing this LL2. If still I want to further decompose that image and want to check whether the quality is still remain there for diagnosis purpose or for transmitting or not, so we go for further more decomposition level, and we tried it till 5th level or 6th level decomposition. Here at 3rd level decomposition, the same process will happen. At this time, this DWT is applied over this LL2 portion, and when this LL2 having like a resolution of 128 cross 128, and we apply discrete wavelet transform over this LL2, then it get decomposed again by half, and we having a low frequency component for 3rd level decomposition, which is represented by LL3, and this LL3 having resolution 64 cross 64. Now we try to check whether the quality of image is retained there, means still we have the quality that must by which doctor can diagnose whether that person having COVID or not, whether this MRI and CT scan is properly distinguishable, like the disease is present or not, means the quality matters in each level of decomposition. So here still we have 64 cross 64, so somehow we are able to see the images. But once we go for 4th level or 5th level decomposition, so we try to convert that 512 cross 512 resolution Lina image into 32 cross 32, or we can say 16 cross 16 resolution. And this is very lesser value compared to actual resolution size of the image. So at the 4th level decomposition, from plot also you can observe the quality of the image is degraded very much. And in 5th level decomposition, you can count easily that 16 blocks in rows and 16 blocks in columns also. And you can feel that the quality of image is literally degraded at very high scale. So we prefer to decompose any of the image till 2nd level, or we can go till 3rd level only. Because at 4th or 5th level, for any of the images, we getting very degraded quality, which we cannot use for further getting all the information what we want to receive at the receiver end. And in the reverse of that process, initially we have seen how the decomposition is happened, and at the reconstructed end, we just reconstructing it from the LL4 or fourth level decomposition to third level decomposition. Then again, this is basically synthesized part, and that was at the transmitter. And when we decomposing the image, that is called analysis part. And this is the reverse process, which we are synthesizing by combining all those values in step by step for lower level of decomposition. So from fourth to fifth level decompositions one becomes, then obviously after transmitting that image from higher level decomposition, the quality get deteriorated. And if we try to reconstruct that image at the receiver end with deteriorated quality, so we are not getting actual image what we have at the input end of the LINA image at the transmitter end. So here we are just reconstructing the third level transmitted decomposed image, and after reconstruction of that LINA image in the reverse process, that from third level to second level, again that LL3, HL3, LH3 and HS3 get combined and form LL2 subband with the H2, HL2, HH2, LH2, and we again combining all these images to form that LL1 portion. And after combining all these first level decomposition of LL1, HL1, LH1 and HH1, we getting our original reconstructed output image from the memristive model or any other model you can use there. But why we try to use memristive model, already we discussed in earlier slides that what the efficient storage it has with the lesser number of logical operations and efficient storage with the less power consumption or area consumption. So before going for its MATLAB programming and simulation result, we just simply try to understand that at what part a memristive model basically used here. So initially we have considering LINA image of resolution, as I already mentioned, that is 512 cross 512 as an original image, and we compress that image by using this discrete wavelet transform. Basically discrete wavelet transform having some wave decomposition factor and bookkeeping factor also, that will tell you that at what level you are decomposing that image. So discrete wavelet transform we using here for the compression purpose, and that compressed data basically we are trying to focus over the approximation coefficients, including the details coefficient also. That complete compressed image data we transfer through this memristive based memory unit. Here in hardware implementation, you can use your memristive crossbar array, where you can supply at the top electrode voltage pulse as per according to your pixels intensity value. And in our case, we are using analytical model of the IV relationship. So we passing this compressed image data through that model. And once that image pass through that memristive model, then we go for reverse reconstructed process, or in doing inverse of that discrete wavelet transform for reconstructing our image. So we use here inverse of discrete wavelet transform, and then we again reconstruct by that inverse process or reverse decomposed process of that reconstructed LINA image. And we just applying the assessment parameter evaluation over this LINA image of the input image and reconstructed LINA output image, that how much PSNR is there if we compare both the results, because obviously this reconstructed LINA image is not as similar as input LINA image. So how much noise or error we may find here, we can calculate these things by using all those assessment parameters of peak signal to noise ratio or similarity index. These terms we will calculate. So in this decomposition and reconstruction, what I try to mention there, that this decomposition comes under the analysis part at the transmitting end, that we are having some input image here, and we applying low pass filter, high pass filter first at the rows of that images for filtering. And once it get half by 2, then we are applying low pass filter, high pass filter for columns, and we come with the 4 subbands at each level of decomposition. And this LL will tell us the approximation coefficient and remaining LH, HL, and HH will tell us details coefficient. So all this coefficient will stored as a wavelet coefficient parameter, and we use this wavelet coefficient parameter to our model. And once we store that values in our model, then we go for reverse reconstruction of that process, and we tell us as a synthesis process of two-dimensional discrete wavelet transform. And there we combine all those low frequency component and high frequency component for reconstructing our original image, and we call that image as a reconstructed output image from memory stream model after doing all this inverse process. In this decomposition level, we try to understand that how basically this complete vector in that code part will form. Initially, we have, let us suppose here X is input image, and we applying here discrete wavelet transform. So it get scaled by half, and we having CA. C stand for coefficient, A stand for approximation. So for first level decomposition, we having CA1 and details other three component, that is LH, HL, and HH. All three component is stored here as a detailed coefficient of first level decomposition. If you go for further decomposition, so we apply our discrete wavelet transform on this low frequency component only, and that is called approximation coefficient CA1, and we again get CA2, that is half of that scale, and we will get CD2, in which again LH2, HL2, and HH2 component will stored, and this is called second level decomposition. Further, if we try to decompose this till third level decomposition, then again discrete wavelet transform apply over the low frequency component only, and we again get CA3 and CD3. If we combining complete this coefficient, so at very initial stage we come with the coefficient of approximated value, and further we go for details coefficient value of third level, after that second level, and followed by first level. This complete value is stored in C, and this C in MATLAB we call it as wavelet decomposed vector. This vector having complete value of that single one image, whether you are using image of higher resolution and lower resolution, the complete information of that image is stored in this wavelet decomposition vector. And here I shows as bookkeeping vector. If we type in command window that I, so it tells you that, let us suppose I am doing third level decomposition. So it form one matrix, and it will write there 3 cross 2, and the 6 values are written here. In the first row they mention 512, 512. In second row they mention 256, 256, and in third row they mention 128, 128. Means in bookkeeping factor we come to know that at what level of decomposition how much which resolution parameter we may find of that particular image. So bookkeeping factor tells us about the level of decomposition, and wave decomposition vector storing all the values of the coefficient which we store. In this pyramidal structure, we can see that n cross n image if we have. So for first level decomposition, that image directly get half from row wise and from column wise. Further, for higher level decomposition, if we go, so it getting again half, and at the end we getting 4 cross 4, 2 cross 2, and 1 cross 1 pixels image at the end we have. So it forms a conical structure in the pyramidal form. And this is a very famous structure for whenever we talked about the discrete wavelet transform operation working principle. Like assessment parameters will discuss, because at the end, if we want to judge the quality of the output image, so we should go for these assessment parameters for understanding whether the image clarity is that much good or not, for diagnosis purpose or for detecting that object or face recognition. So these few parameters we are on the basis of which we can clearly tell that whether reconstructed image is of use or not. So first on this compression ratio, that compression ratio is basically defined that the number of zeros element and the input to the number of zeros element at the output end. Sometimes if we introduce some zero element from our end by considering threshold values, which we will see in coming slide, that how those process also going on. And it's really very interesting that if we try to reduce the size of the image, or if we try to save our bandwidth, so how we can go for additional compression also. Another point is here that quality basically PSNR tells us about the quality of the image, that whether the image having good quality or not depends on the value of the PSNR. If peak signal to noise ratio having higher value, means the quality of the image is good of reconstructed output image, and if it is not much higher, so we can say that reconstructed output image having poor quality and we cannot use for application part of, if I'm using medical images, so we cannot go for diagnose part, because the quality of image is very deteriorated at the reconstructed output end. One more parameter is here, that is mean square error, and we already have seen that the importance of root mean square error in antenna subject, that satellite communication antennas, that how much important, and on the basis of it we effectively calculate the values of the and performance of the this antenna or satellite. So these are the important parameters. One similarity index is new term, maybe for those who never comes in the image processing part, that in case of similarity index, we having three different parameters as mentioned here, L, C, and S, where L stands for luminescence, C stands for contrast, and S stands for structural similarity between input and output end. So we just multiplying these three values for calculating this similarity index, structural similarity between input and output image. But if we go in depth of this similarity index, so one paper is there with the complex mathematics, that how they define this similarity index on the basis of luminescence, contrast, or structural similarity. You may prefer that paper also for better understanding of that SSIM mathematical portion. Here, for understanding that on what basis we are calculating the similarity index, so we need to know that luminescence, contrast, or structural similarity parameter on the basis of phase orientation of that image after construction of that output image. How we can relate these three parameters with the input image on the basis of phase orientation, we calculate this similarity index, or we can say structural similarity index. So in our case, basically in discrete wavelet transform, we have number of families in the wavelet, and each wavelet having number of series. In case of her, basically one scientist is there who invent this Haar wavelet. So it having waveform of a discrete waveform like 0 and 1, direct pulse generated waveform. But other than this Haar wavelet, we have debauchees, simulate, coeflate, bi-orthogonal, reverse bi-orthogonal, and phasor provoking. So all these wavelet having a series of different wavelets also. So we are just optimizing. Let us suppose if we talk about debauchees having different versions like dB1, dB2, dB4, dB3.2. So out of all this series, this dB2 is optimized for our result. In case of simulate also, we having many more number of series, out of which Sim4 is optimized, giving optimized result for medical image processing or linear image processing by using Humble-Steve model in our case. Similarly, for coeflate, out of complete series, we getting optimized result by this coef2. In case of bi-orthogonal, having there are also number of series, but we using BIOR. Actually, these are the commands which we can use in wave menu tools in MATLAB also, or we can directly use in the coding part, that in the syntax they mentioned that which wavelet you want to call for your further processing of the decomposition by using discrete wavelet transform. So you can mention there this name instead of complete bi-orthogonal. The syntax to work like that series particular BIOR 1.5 we try to use for bi-orthogonal wavelet operation. Similarly, for reverse bi-orthogonal, we using our BIO 3.1 series because it giving optimized result as compared to all other series. And at the end, phasor provoking, we using its FK14. we having different waveform for each wavelet, and as we can see in this values also, that similarity index, or we can say PSNR, we getting higher in terms of image quality. Directly we say that if PSNR value is higher for Haar wavelet, means the reconstructed output image for Haar wavelet based image is higher compared to all other wavelets. So we prefer Haar wavelet at our first consideration. And what I'm going to show in this MATLAB programming is based on that Haar wavelet only. For the other wavelets also you can use in splits of Haar, then they can call that particular waveform. And if I am telling that for my image, for my operation or for my application part, that Haar is suitable, it doesn't mean that other debauchery, simulate, coeflate, and other phasor coroverkin wavelet is not that much useful. They are also giving best result in their own application part. Means for it depends which wavelet you are using for which application part. In our case, Haar giving best result, bi-orthogonal, sometimes coefficient also giving best results. So it depends application to application. So we cannot comment that Haar is best and other is not best. But in our case, Haar giving better results. So we are trying to use Haar wavelet compared to our other wavelets. So in MATLAB programming, initially we call this Lina image, as we can see that clear, close, and CLC. If we are you all use MATLAB platform, so we know this basic that they try to clear all these command window functions and the workspace specifically, and then we calling at the 4 line that Lina image, and then we also know that the by default logical operation is double instead of like if we talk in terms of data type. So here we have unsigned integer, character, string. So for logical operation we have integer or float. So floating we have two terms, whether we go for single and we go for double. So in MATLAB command, for any logical operation they by default considering double for float operations. And obviously, as I mentioned, that memory register having capability to store value between 0 to 1. So at the end, we normalizing this value or sampling this value in between 0 to 1. So we need double operation for all double data type for all the arithmetic and logical operation. Initially, we call this grayscale Lina input image of resolution 512 plus 512. As we can see here that we call this input image, and we use this Haar wavelet for discrete wavelet transform, and we're storing all these values in LL, LH, HL, and HH component. We're trying to save all this value in this coefficient COEF 1. I'm just trying to show you that how much degradation in the image with this data type effect that we observed in step-by-step form. So here I'm just trying to say that that's the first level decomposition if we use double data type. So I'm getting the reconstructed image in such a form. And therefore visualizing in uninteger form unsigned 8. By 8 I'm writing here means why I'm choosing unsigned integer 8 data type for reconstructed this image for visualizing clear to human, because unsigned integer 8 bit here, as I already mentioned, that grayscale having range from 0 to 255, means per pixel having assigned bit is 256 scale we can use, and 256 is nothing but 2 raised to power 8. So we can say per pixel we having 8 bit, and here that's why using unsigned integer for 8 bit. So we convert this data type from double to unsigned 8 bit position. What happened at the first level decomposition I already mentioned in the earlier slide, so you may better understand with the coding part that how it goes to happen. For second level decomposition, again what we do that firstly we apply this TW command over the Haar wavelet, and we store all these values over there in second level decomposition LL2, LH2, HL2, and HH2 coefficients, and we taking all these vector in coefficient 2 vector for storing the complete value at a time. and we can see this image of second level decomposition by IMSO command. And by varying the data type from double to uint8, you can clearly observe that what the picture you are getting. And here, as we go for higher level decomposition, the image get brighter. In case of TQWT also, as we go for higher level of Q, so or for higher level of decomposition by varying the value of J, we'll see in coming slide. So we getting brighter image. After that, we try to observe the complete image by combining both the first and second level decomposition. So here we can see these 3 details coefficient is of first level decomposition. These 3 details coefficient is of second level decomposition, and this is our low frequency component we achieving after doing till second level decomposition by using discrete wavelet transform operations. This program is still third level decomposition. So again, we do the same process over the LL2. As we can see here that we are applying this discrete wavelet transform command over the LL2 component only by using this hard wavelet, and we're storing all those coefficient over this coefficient 3 matrix or vector, we can say. And then we can see that double data type is look like this, and the third level decomposition with unsigned integer is look like this. Here the low frequency component again getting brighter, and the size of this third level composition is 128 cross 128. When we try to see combined picture of this first, second, third level decomposition, so we can do like this, and we can see clearly that what's step by step is happening basically by using this discrete wavelet transform. If we go for further storing this complete image in our memory strip model, so basically this is the input to the memory strip based memory unit, and we use this proposed memory strip equation as threshold voltage programming voltage, which is already mentioned in earlier classes, that how this analytical model is designed. And then we try to store all these pixels value by using this memory strip analytical model here. We just simply code this for the equation in this part for storing those values. And once we have done that, so we go for inverse process after normalizing that value, that we reconstruct that image once we store that image in the memory strip model. So the output we get like something this at the third level decomposition, and we resize that image from rows to column, as we mentioned here that the reshaping happens what we reconstruct the current from the memory strip system is stored in IC, and size v comma 1, size v comma 2 tells us the size of basically for rows and columns, as we decided that was the number of vectors will assign that rows and complete columns. So that size will tell that at what level this I and j get varies, and after that we are just doing normalization by dividing with the maximum value. See here, Z is specified as the max of max IC, means whatever the output current you may get, you have to take maximum of the rows and maximum of the column, and whatever the value you at the end getting, that is complete maximum value of the complete reconstructed output image, and you divide that image by that maximum value, and you go for reconstructed process. For visualizing that image, you should use that unsigned 8 integer, and the logical operation by default in MATLAB going with the double data type. These are the reconstructed output process, as I already mentioned in the earlier slides also, that how this third level decomposition get combined with the second level decomposition, and the resolution of the image get converted from 64 cross 64 to 128 cross 128 from third to second level decomposition. From second to first level decomposition, we using again the inverse process of IDWT command, as we can see in line number 170, that we using IDWT command, and the same wavelet we are using what we are used at the decomposition end for reconstruction purpose also. Here again we go for from second level to first level, where that 256 cross 256 resolution image get converted into 512 cross 512 for further reconstructed output image. as we can see that this is reconstructed output image, but the quality of the image get deteriorated much more compared to what the input image we are giving. So this is our compressed Lina image, which we stored in memory stick system after third level decomposition. One more command is here, because what I have shown you right now is step-by-step process. We can use wave decomposition technique by using syntax wave deck, and here we can directly mention that third level decomposition we need. So in this text, instead of DWT, we directly type wave deck 2. So it will understand that we try to decompose wave for third level decomposition using her wavelet, and we give already our input image here. At the reconstructed end, we're getting output as similar as what we get after doing all this loop process, and for complete third level, fourth level decomposition process, the image similarity will be same, and we're getting the same value of PSR, SSIM, and similarity MSE there. So in this form, we understand that what's the actual process of MATLAB programming with the step-by-step simulation result we have seen till now. Now we see the effect of brightness over that reconstructed output image. That, let us suppose I'm getting that image after third level decomposition. So obviously the image quality is poor. But if I want to save my bandwidth or power consumption should be lesser for less number of resolution, means if I am talking about third level decomposition, that means I'm using 64x64 resolution image. So for that much small storage capacity with a less computational task, with a lesser consumption of area, and with a high efficiency, we can think to store that much power, like the consumption of power we need to require use lesser if we go for third level decomposition, and we can enhance the quality of image at the receiver end by taking some circuit of amplifier or adder of the particular value by multiplying or adding that value to the per pixels intensity of that complete image. So what we what we observed that for reconstructed image, in case of Lina, we add constant value 52 to each pixel, and we enhance the quality of image. This 52 is optimized value. If you think like, if we adding 52 and we getting a much higher value of PSNR compared to what the actual reconstructed image is giving, so we may go for 100 or for 152. So this will not the case, because if we increasing the value from 52 to 100, or from decreasing the value from 52 to 40 range, so the again the PSNR get deteriorated, because this 52, or sometime in some images multiplication of 1.5, multiplication of 2.3 is giving optimized result of that particular image. So these are the optimized results which we can adjust at the receiver end for enhancing the quality of image. Here we can see for her wavelet we are getting 82.67 increment in the quality of the image, and for debauchery simulate coefficient by orthogonal, reverse by orthogonal, as well as for feather coloquine, everywhere we are getting enhancement in the quality by double, a kind of, means 80% or more than 80%, means it is almost double the quality or enhancement in the quality of the image, and that much we can afford by adding some amplifier at the end of receiver or some adder there, instead of wasting the bandwidth or the power consumption what we try to save by using memory stick crossbar. So these are the some benefit point we observing by this effect of brightness for different wavelets. After that, we will see that what the effect we observed from first level to sixth level of decomposition of this Lina image. So from this plot, as we can see, for different level of decomposition, the quality, see here I'm mentioning here PSNR. PSNR already represented what? The quality of the image. So for first level decomposition, the value of PSNR as well as the similarity index, structural similarity between input and output is higher. As we go for second level, third level, so obviously the value of PSNR as well as similarity index get reduces, but it is minimal amount. Means let us suppose for first level decomposition, if my resolution, my image having resolution of 256 cross 256. So for second level, it comes to 128 cross 128 resolution image, and still I have the PSNR which is manageable somehow for diagnose purpose or for detecting which person is there at India-Pakistan border. So if that much detection is possible till second level or third level decomposition, so we go for that lower higher decomposition level, because we try to store that image with the efficient form. For less power consumption means we try to save our power. So we try to go for third level decomposition where we can save power, go for lesser complexity of logical and other operations, or we can say we go for efficient storage of that in our memory stick crossbar system. So till third level, we can see the quality is degraded, but not that much that is not bearable. So till third level decomposition, we getting PSNR when we adding some brightness at the receiver end, this much. And at fourth level, we will see fourth level means we try to store 512 cross 512 image into 32 cross 32 bit, or we can say crossbar, or we can say resolution. So that much decomposition is not acceptable, as we can see in this plot, that the quality of image is degraded very much. So we try to stop at second or third level decomposition. Here the green line shows the effect of brightness, and here blue line shows without brightness. So effect of brightness also giving very much good quality of images compared to without brightness. So we prefer to add some brightness at the end of receiving end. In second plot, we can see the threshold technique, what I mentioned earlier, that additionally we introduce some zeros in our complete pixels. Why? Because we try to remove the redundant data, or those component or the pixels value which is not affecting that much. Let us suppose if I am having grayscale image with the scale of 0 to 255, and I want to compress that image by considering some threshold value of 10%. So I'm just considering the maximum pixels value of the complete image. So let us suppose I have maximum pixels value of 255. I'm taking 10% of the maximum pixels value, that is 25.5, and I'm just adjusting my threshold value to that 25.5 threshold value, and the values which is higher than this 25.5 is passing through that model, and the value which is lesser than 25.5 is replacing by zero value. So in this way, what we trying to do, we simply try to save our bandwidth, or we try to save the area storage, because this small redundant data we can easily remove by adding some additional zeros also. But here what we observe, that we can compress that image by addition of zeros till some level, because if we are adding more than 50%, so the complete quality of the image get deteriorated. So as we can see, for 10% of that image we deteriorated this much. For 20% image we deteriorated that quality of the image in terms of PSNR this much. And as we go for higher value of threshold, like 30%, 40%, 50%, so it get exponentially decreased in the quality of the output, reconstructed output image. And that's why we try to decompose the image or the threshold value till some marginal level, and it will decide whether the quality of image is whether diagnosable or not. As per according to that, we will decide the level of decomposition, as well as we decide the level of compression by doing some external addition of the threshold value. So these 2 points I mentioned here, and one more point we can observe in second plot, that first, second, and third level of decomposition is nearby, but for fourth level decomposition, the quality at the initial point itself degraded by higher amount, or we can say here, as in last point already mentioned, that the maximum degradation in the quality we observe from first level to sixth level by 41.66% for the same value of compression ratio, and that will be 1. So this much degradation we also fourth level decomposition, and for fifth and sixth level decomposition, the value get overlapped with each other. So for Further, when we go for biomedical images, so there we use CT scan and MRI. For those images, we go for fifth level decomposition, because in Lina image we already observed that fifth and sixth level getting overlap, because the values get almost saturated in terms of poor quality of that image, because fifth level decomposition is not of use for diagnosis purpose. So here, first I want to tell that what models Memristor basically trying to replace. One is our application specified integrated circuit, which is mostly used in biomedical healthcare instruments, CT scan or MRI. If we talk in terms of communication channels or radar or satellite communication, also having most of the circuit based on this application specified integrated circuit, because we having here microcontroller as per according to our control our need, we code the programs, and accordingly that for the particular application that integrated circuit will work. Other circuit, that is CMOS technology, basically replacing by Memristor. And what's the point? We already have seen in our previous slides. One more circuit in one paper they mentioned, that is conventional flip-flop used in sequential circuit. Memristor model giving much more best result compared to what the flip-flop in sequential circuit is giving. So in this workflow, I just want to mention that this image processing simulation part step by step, that what actually we are doing. So first we are calling input image, as we have seen already in our programming part of MATLAB also. Then we use that wavelet transform, and then we go for image scaling and normalization part, that we store all those values from 0 to 25 range, in between 0 to 1 range, so that ranging of the value from 0 to 255 to 0 to 1 is called as normalization or scaling in this range. We can range it from -1 to 1 also, but we try to store all those values in between 0 to 1, because it will give much more efficient. And one more use of it in CNN we'll see in coming slides, that what's the importance of 0 to 1 storage in activation functions, on base of which sigmoid function is working. So basically for that logic we using that in between 0 to 1. After that we go for wave decomposition vector that pass through the Memristor model, and inverse of the process of wavelet transform we have done there. And what the thresholding applied I mentioned is discussed, is implemented after inverse process, and then at the end we getting final reconstructed output image. So these are the result which is already submitted in IEEE transaction. This is under review. That here we can see that we are using MRI and CT scan images by using two different wavelets, that is R and bi-orthogonal, also giving good results. So we just having results of these two wavelet used images. And as we can see here, that for first level decomposition the quality is deteriorated, no doubt, but having marginal loss here. In second level also we can use those images for diagnosis purpose, but for third level decomposition the quality degraded at a higher rate. And if we go for fourth and fifth level decomposition, so we can see we are clearly seeing the boxes instead of the image quality. We clearly count this at the end. Fifth level decomposition, we clearly count that the number of boxes here of 16 in rows and 16 in column, which trying to represent decomposed image of bi-orthogonal wavelet CT scan or HAR wavelet based CT scan till fifth level decomposition. So this kind of observation we have done till date in biomedical applications. One more work is done in CNN part, which we will see in coming slide. Here we have some quality effect by compression ratio or brightness. We can observe in this plot that we having this image of 7 different wavelets basically, and we try to observe that which wavelet out of our debauchee, simulate, coefficient, bi-orthogonal, reverse bi-orthogonal, and phasor correlation, which wavelet giving us the highest value of PSNR and other assessment parameters like similarity index and lesser value of MSE. On the observation of these values, we come to know that HAR and bi-orthogonal will give the highest result. as we can see here that the circle is shown by R, and here the value of R is higher. If we go for the tabular form, then we come to know that here also R and bi-orthogonal giving the highest value. An inset image will tell us about the effect of brightness, that whether the brightness is giving high impact on the R wavelet or not, or on other wavelets also. We can observe from this diagram that the effect of brightness is also observed in each and every wavelet based reconstructed output image. Reason behind R is one more point observed, that if we didn't add any external threshold values based zero component, still if we calculate the compression ratio, so in R wavelet case, the compression ratio will be 1 for level 1, level 2, level 3, level 4, level 5, as well as for level 6. But in case of other wavelet transforms like Debauche, Simlet, coefficient by orthogonal, phasor, Kurobokin, or reverse by orthogonal, this will not constant at 1, means the addition of the some noise, or we can say some external addition of the zeros is happen inside model also by using this wavelet, but this will not happen if we use R wavelet. So this is one more reason why R wavelet giving best result in our case by using our model for image processing. Here we try to observe that how much percentage of data compression is happened for different level of decomposition. As we have seen here, by using R wavelet and by orthogonal wavelet for MRI and CT scan, we're getting highest value for CT scan in a R wavelet when we use R wavelet for CT scan. So for first level decomposition, we compress that data by 47.81%, and this is very higher value. If we try to diagnose some person, and we can store somehow by half of that complete storage efficiency. So obviously power consumption also get reduced by half, and with this part of saving, we can also process the image for further diagnosis or for different applications. So this much higher percentage of compression we observed from administrative model. In other level of decomposition also, we can see that it get increased till fifth level decomposition. The image get compressed by 91.79%. But we also need some information. That's why we go for some marginal value, that is maybe for second or third level, where we can compress the images by 69% or 81%. As we can see here, that 69.34% or 81.84% we can compress that data. Similar things we observed in terms of bi-orthogonal also. So this is the basically formula of data compression, that taking size of the input image and subtracting it from the size of the compressed image at the different level of decomposition, and divide it again by the size of the input image, multiplying it by 100. So we come to know that how much compression of data happened at this different level of decomposition. Here we have we can see that plot for the quality with the compression ratio. As we can see, we as we go for higher level decomposition, then the quality of the image get deteriorated, and as we go for higher compression also, means if we adding higher value of zeros for 30% and 40%, then the degradation rate is higher, and at the end we can say to 70 or 80, it gets saturated, and the quality of image is degraded like anything, and we cannot use those images for further diagnosis purpose. Inset images tells us with the different decomposition level how this degradation in the quality we can observe with brightness and without brightness. With brightness, we just add simple amplifier and some adder at the receiving end, and we enhance the quality of the image in very higher rate compared to what we observed in this black line without using brightness effect. So this is decomposition level 1 value of PSNR and SSIM, and as we go for higher level decomposition, this value get decreased by some end, and for third and fourth level, fifth level, this value continuously get deteriorated. Similar observation we have done for R wavelet also, as we explained in by orthogonal part. for CT scan, and for MRI also you can observe for different decomposition level. Let us suppose if we are talking about decomposition level first, so the highest value of PSNR, which indicates the quality of the image, is very good for first level decomposition, but for second level decomposition it get deteriorated, as we can see observe here that by 10 or 20% it get deteriorated for second level decomposition. For third level decomposition again this get deteriorated. For fourth and fifth level decomposition the degradation observed much higher compared to first three level decomposition. And this insert image again here shows the effect of brightness, with brightness or without brightness. The value of PSNR as well as structural similarity index is getting degraded for the different decomposition level for MRI image also. In next part of work, we go from discrete wavelet transform to tunable Q factor wavelet transform, because we want to study that oscillatory behavior of those images also in terms of signal. So, and here we use one more analytical model is published by a senior. So, this model we are going to use in this tunable Q wavelet transform vector for storing. The purpose of this storage is for CNN model also, means we are trying to cover that activation part by using its window function, which is already mentioned in earlier sessions of this FDP program. So I'm just starting my this second part of work by CNN model, that what actually we're trying to work here. See, artificial intelligence is, I think it started in 1950s around. So he, on that time, people try to think that machines should behave like human behavior, that what the labor is doing in industry and all. So instead of doing that laborious work by human, we use some machine which work on the command that place that product from one place to another place and all. For that part, we introduced that artificial intelligence initially in 1950s, where we our objective to train machine as a human behavior. Later is around 1959 or 60s that machine learning part will come, and there we try to mention that the machine should learn from their previous mistakes, that what they have done. And in machine learning there are three processes, three steps, as here mentioned also, that it having pre-processing is of the work first. If I talk in terms of image processing, so let us suppose I have bunch of images and I want to find whether this image is of person or is of animal. If it is of animal, then whether it is cat, whether it is dog. So first it passes through pre-processing step. After that feature extraction will happen, that the eyes or nose is like similar to human beings, or is similar to elephant, or it's similar to cat, or it's similar to dog. As per according to this feature extraction, it goes for further feature selection, and then at the end we get classification. In case of CNN model, in case of deep learning, the process is different, which I will tell you in coming slide. But here I want to mention one point, that in case of machine learning, the training time is lesser or testing time is higher. But in case of deep learning, training time is higher, because we having lot of number of layer of convolutional as well as that pooling layers with the fully connected layer and the softmax layer. So the bunches of layer in case of deep learning is very high. So when we training the data in deep learning part, so that time consumption should be very high. But once if we trying to classify those data by using different models we have here, like ResNet 50 models, AlexNet, VGG16. So there are so many models by which we can classify the image, whether it is cat or dog, or in my case, in our case, what we are doing in our lab, that is based on a small data set and large data set, whether the image having COVID patient or not. This kind of classification we are trying to do by deep learning. So in deep learning process, the training that process is consuming higher part, but the testing time is lesser. But in case of machine learning, the training process consume lesser time consumption, but the testing part consume more time. These are the basic differences. And in deep learning, algorithm inspired by the structure and the function of the human brain. Basically, in deep learning, we have multiple layers, which is almost behaving like or similar to human brain. But in machine learning, we simply train the machine that how it should work and how it learned from its previous mistakes. So this kind of models we have here of a neural network, and one model we can design for machine learning purpose. Here one graph I have added where we can easily see that machine learning should use when you are going for a small amount of data. If we are going for large amount of data, then machine learning will not perform that much better. So better to go for deep learning process if we having large amount of data, because the performance will be higher if we use deep learning in case of large amount of data. Machine learning will be okay if we are having a small amount of data and we just want to check its performance by using our model. So these are the things here. And the main hurt we can say in the CNN is activation function that activate the neurons of that CNN model or convolutional neural networks. So basically in activation function, what happens that initially people use that sigmoid function with this equations I already mentioned in this table. Later we having some problem with this sigmoid function that it only defined for 0 to 1, and in meanwhile it also vanishing this gradient values. So for resolving that issue of missing this gradient value, we come with a tanh, or we can say it a hyperbolic tangent activation function whose range is from -1 to 1, but it also not giving that much higher impact on that vanishing gradient. So we introduce one more activation function that is ReLU, and this is called rectified learning activation unit, and this will give better result compared to these both sigmoid and tanh, but still it having vanishing problem with of that gradient. So what we are just trying to do, we using our window function. One more paper published already in recent that they replacing this ReLU with their administrative waste ReLU function, and they getting higher impact of accuracy compared to ReLU based function. We are comparing our result at the initial stage with the sigmoid function, and we also getting better result. What we are doing that we are taking 3-bit numbers like 100001, and we are updating its value by differentiating that what's the updated value of the corrected output and what we actually giving as an input. We update each every run of that cycle, and we run that cycle 4000 times, let us assume here, and then we are adding if we have some biased input there, so we can consider it as a noise also. So let us suppose we having some biased input also here. After updating all these weights as considering as output, and then adding all this weight with this bias voltage, and we getting at that output output of that complete pattern of 100 and 001. So better to understand this way that input we are giving 001, 011, 101, and 111. We try to find actual output of for those images in this corrected output. We already initially mentioned if I'm getting input as a 001, so my output should be 0. I mentioned these things at the initial stage. But when we use CNN model by using a sigmoid function of activation function, so the corrected output is nearby 0.0102. That is not actual to very equal to 0, but once we are using that memristive based window function, so we get 0.0067592. that is much more closer compared to already what mentioned by sigmoid function. And this sigmoid is inbuilt command or inbuilt activation function of the MATLAB, and it having many more other disadvantages already, as I mentioned that it having vanishing gradient issue that will not issue for the memristive model, and it will give much more accurate result compared to sigmoid function. In case of 1011 pattern also, we can observe here that sigmoid giving 0.0083, but in case of memristive model we are getting 0.000627. that is much more accurate compared to sigmoid activation function. For other two pattern also we observed that if we mention that 101 pattern and for 111 pattern, our corrected output will be 1. but for when we using sigmoid function, so they mention value 0.9932 and 0.9917. But in case of memristive based window function, as an activation function, we getting value much more closer, that is 0.994 and 0.994 in both the cases. So the accuracy by using this window function of memristive based model is more compared to sigmoid function. And this multi-layer neural network I presented here for explaining little part of CNN, that at the initial stage we have multiple number of input in terms of digits or in terms of images. So what happens in class of ResNet model or AlexNet model, we having number of layers of convolutional with max pooling layer, or sometimes using average pooling layer, and we pass this layer filter by filter, means we having one convolutional layer having number of filters. So you have to decide that how much, like in case of AlexNet 50 we have less time, so we try to cover it as fast we can do by understanding the basic concept, that what I try to deliver here, that AlexNet model having, let us suppose, 7 layer, out of which 5 layer is considered as convolutional neural network and 2 layer is considered as fully connected layer. So it depends at your end that in your model how much layer you want to take from the convolutional neural network, how much layer you want for max pooling layer, whether you want to take max pooling or average pooling or global pooling, what these parameters are. I'm just showing in my coming slide that what these parameters are. And at the end we having some softmax layer or fully connected layer, means at every layer every dot is connected to complete, as we can see here also in hidden layer, that each dot is get connected to all the we can say layers of the previous mentioned layer. So this kind of study we can we can study in this CNN model, and at the end we are just adding this fully connected layer for just classifying those by using softmax layer, whether this, let us suppose I am just using right now COVID images of chest X-ray. So I just want to know whether that person having COVID, whether this person having pneumonia, whether that person having COVID or not. So let us suppose I am just classifying my output in 3 class, that whether the person having COVID, non-COVID or pneumonia. So at the softmax layer, output of softmax layer will be 3: COVID, non-COVID and pneumonia. So this will be taking at output layer end. Basic of TQWT is similar as what we have at the discrete wavelet transform, but the basic difference that we can study here, the oscillatory behavior also. And this oscillatory behavior basically depend on this alpha and beta parameters, which is basically transfer functions of that low pass filter and high pass filter. Basically in TQWT we having 3 parameters, that is Q factor, one more R is there, that is redundancy, or we can say that redundancy is oversampling rate of that image. And third is J. J will tell you about the level of decomposition, that at what level of decomposition you are going to work. Steps are the same, that at each level of decomposition, low pass filter and high pass filter is applied over the rows and column of that images. These are the basic steps of flow that compute discrete time for a transform for the input images, and then we pass this complete image for the low pass filter and high pass filter for analysis part. Why this analysis part? Because we are talking these terms at the transmitting end, or we can say at the decomposing end. Once the decomposition will happen here, then the scaling of the low pass and high pass component is stored, and it pass through our model or channel, and then again we go for reverse process, that is called reconstructed process, or here we can say we use synthesized filter banks for reconstructing all those things, and we just optimize this till the values for the Q, R and J we finalize, like what the optimized value of Q, R, J, for which I'm getting the highest value of peak signal to noise ratio and structure similarity with the lesser value of MSE. So this kind of observation we have made here in TQWT task. and we get the higher value of PSNR compared to what we are getting in case of discrete wavelet transform. That, as we can see here, that for MRI image, and there we are getting by using discrete wavelet transform around 18 dB, but here we are getting 23.6108 dB. And in case of CT scan also, there we are without brightness, we are getting only 12 dB around, but here we are getting 17.9064 dB. That indicates that the quality of image getting higher if we go for tunable Q wavelet transform part. So we use this TQWT for decomposition purpose, and that decomposed images further pass through CNN model for further classification of the image, that whether this person having COVID or not. So what the need of it already mentioned in earlier slide also. Here again I am just mentioning the limitation of general purpose digital system, that it having some Murray's law, that approaching toward end of the Murray's law, that the number of transistors is getting double every 10 years or 1 decade, and the data transfer is also very consuming much more bandwidth, and power consumption is also higher, also exploding that data set size. So we just want to replace all those FPGA, CMOS, transistor, and ASIC based circuit by memristor crossbar array. Why? Because it is promising approach for deep neural network also. That complete layer by layer, we can replace that layer by layer convolutional network which is based on CMOS by memristor stacks. And we also consider that memristor crossbar by this vector matrix multiplication that performs similar as DNN. And this VMM can perform a single step in memristic crossbar array. As I already mentioned in my earlier slide, that for CMOS multiplication and addition operation consider 20 steps, whereas in case of memristic crossbar only 2 steps is considered for that complete logical operations. So this kind of advantage we have in case of memristic crossbar for going toward this CNN model. These are the basic what I already mentioned, that in deep learning we have some feature learning section where we having activation function, convolutional layer, and pooling layer. So the details of it you can go through this cited papers also, so you can come to know that how it's functioning. Our objective is to take this input chest X-ray images and comment that whether this chest X-ray image having of those person, whether that person having COVID, non-COVID, and pneumonia. This kind of classification we try to observe from that part. In case of facial recognition also, we are motivated to work that we have taken one pic of my senior, and we try to store that image in our memory strip crossbar. So how we can do this? That we consider that complete image as the input space, and we divide it into 4 parts and consider one part as an inhibitor region, and we again decompose this image in half of that part, and we consider each block as a receptor block region. Then again we divided it into multiple regions and consider one pixel's value as a synapse input region or single pixels, and we store this single pixel's value as V11 in the giving like as a voltage pulse supply in the memory strip crossbar, which is already discussed by sir that in our earlier session, that how it basically work to store the values. So we just considering this each pixel's value and this memory strip crossbar as a voltage pulse supply with that particular intensity for the storage. And see, as what I said, that each layer of the output is connected to the backend layer of the input in CNN model. So this kind of observation we can get here, that for first second until the end of the layer, that is VIN, is connected to the end of that top electrode, wherever at the bottom electrode we are giving supply. So when we just reconstructing, or we are taking that complete information of the complete block of receptor block region, so we getting that information in VR1, where that all information is stored for this particular image of that receptor image block. So here once we collect from VR1 to VRM, we store this value in one voltage mean calculation box, and we calculate one value there, which is considered as a threshold calculation. And the importance of threshold I already mentioned in my earlier slides. That's why we try to use threshold value. So we just taking a threshold comparison. One block is there where we have set of comparator, and we giving our input VRI, what we are just taking as our output from the memristive crossbar system, and we compare those results with the threshold calculation. And we come to know whether this value is higher than threshold, then the value is passed. If it is lower than that threshold, then the value is either 0 or that as similar to what the threshold value we measuring, we can pass that value to the output, and we just invert that value for getting the final output as VF1, VF2, VFN, and we store as in bit form that 0, 1, whether darker or in binary form. If it is in gray form, then we can scale it from 0 to 255. So as per according to our need for the particular specified application, we design this circuit. So that was the part for facial recognition. In convolutional neural network, I just want to mention one kernel steps is there, that at each stage of the decomposition, we use some kernel matrix, which is basically reducing the step of that complete matrix box, that we do not want to transfer complete box of 512 cross 512 from input to output end. We just want to train the data in small boxes. So for that part, we using this kernel matrix, as we can see in this slide. We complete multiplying this complete 2 cross 2 matrix with the initial step, then with this middle, and with this end. So we convert this 4 cross 4 matrix into 3 cross 3, and we reducing the data with the accurate values, because for the particular image we having different set of kernel values, and these all values are decided by the user for their own models. So this part of things we have seen. One more layer is there, that is pooling layer. And in case of pooling layer, as we can see that if we have 4 cross 4 matrix, so for average pooling, we can take first 2 cross 2 matrix and adding all these values and divided it by 4, and we come to know that the average pooling value of the 2 cross 2 first part of the matrix is 12. Similar operation can be done for other 2 cross 2 sections also, and we make average pooling layer. Sometimes instead of calling average pooling layer, we try to use like in AICTE model, we use max pooling layer with that convolutional part of layer, that taking the maximum value out of all these 4 values, that is 25. So it directly considers 25 out of all those 4 sections. And in global average pooling, in some models, people use global average pooling layer. So what they are doing, they are adding complete 16 different values in this 4 cross 4 matrix and divided it by 16, and the output value is considered as a global average pooling layer. These are the accuracy, precision, sensitivity, and specificity formula, which is calculated on the base of confusion matrix. Here one more confusion matrix is there, which tells you about whether the number of true positive and number of true negative, number of false positive and number of false negative values are there after the calculation of whether, let us suppose I am just considering here a small data set with having value 2193 X-ray images, and in case of last data set we having 5267 X-ray images. So how much correct measurement is done or classification is done by our model, or how much false measurement is done by our model is dependent on this true positive, true negative, false positive, false negative. And on the basis of these values, we calculate this accuracy, precision, sensitivity, and specificity. These are the steps for classification that call images, optimize the value of TQWT on the basis of Q, W, R, and J, and further go for storage of the reconstructed output image. And we go for training of the 30% of the complete image, and then we go for the validation within 70% of that data. We have done this classification by using 2 different models, that is ResNet, Residual Network 50, and AICTE model. And we're getting a much more better result by using AICTE compared to ResNet model. And at the end, we come to know that how much COVID and non-COVID images we have in that complete data set. These are the values of small data set and large data set. We're getting higher accuracy by using our model compared to few of the reported data by using the same data set. And these are the confusion matrix where the true positive, that COVID person having COVID, and our model also that said that this person actually having COVID is 586, and the person don't having COVID, and our model also predicted that person is normal, not COVID. So that number of images is 591. The person having COVID, but my image unable to predict that that person is COVID is 10 images there, and the person is normal, but my model predicted that person having COVID is 5 number of images there. On the basis of this criteria, we calculate this accuracy, precision, sensitivity, and specificity. This value is for ResNet 50. Another is for AICTE. The calculation part and the logical operation behind this are same. So these are the conclusion that we use memory state crossbar for data compression, and the effect of brightness also observed there. And 2D discrete wavelet transform is used for the maximum degradation from first to sixth level composition. How much percentage we already have seen in our previous slides. Out of complete wavelets or 7 wavelets, Haar and orthogonal, giving best results. And we use that activation part also, that sigmoid function is not giving that much accurate, but our memory state based window function giving much more accurate result in activation part also. And we're using TQWT with the optimized value of Q equals to 4, R equals to 3, and J equals to 2 for classification part further using AICTE and ResNet model, and we're getting better result by using AICTE. Thank you and for your attention, and if you have any query, then please ask. Thank you.
Good evening, ma'am.
Yes. Yes.
The session is very informative, ma'am.
Thank you.
Ma'am, I have some 2 to 3 doubts. Shall I proceed?
Yes.
Ma'am, in slide number 7, there are fitting parameters, no, ma'am?
Slide number 7.
7, yes, ma'am.
Yes.
Ma'am, actually, which model is used to approximate these IV characteristics, ma'am?
Basically, we are extending this model from Jacobic model. If you heard about the different type of models we have, so basically this model is very similar to Jacobic model, but we try to just measure our yttria based oxide, like Y2O3 is used in our lab as a memristive resistive switching material. So for performing its IV operation similar to this analytical model, we are extending the work from Jacobic model to here. In Jacobic model, what happened, the percentage rate is little higher compared to proposed analytical model, which is done by our senior. So here what happened, that we just giving some extra parameters, that is A1 and A2 for experimental fitting. What we are getting by that IV curve of the yttria based oxide, we try to trace that actual path that is not observable accurately from Jacobic model, but that is much more accurate if we use these values A1 and A2 in B1 and B2 as mentioned here, the numerical values of it in that proposed model. Is this your doubt is clear?
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
Mhm.
Ma'am, I have another doubt. But there are so many Oxfam models, no, ma'am.
Where?
So particularly for image processing application, which material we have to select, ma'am? And for image processing application, do we want to look after the switching speed, leakage current, and all those parameters do we consider while selecting the material for fabrication?
First, yes, it depends that in what application you are going for. I'm also going for different leakage current value, and in second model also my senior specify the range. We can switch for A1, A2, B1, B2 parameters. We can go from one end to another end. But what I observe in my case, for different values, if I'm going, so I'm not getting that much appropriate value of PSNR, or we cannot getting appropriate values of the quality that what I actually needed. So what the reported values is mentioned in this paper, this actual values giving me the optimized result in case of reconstruction of the output image. If we change the value of leakage current and all, so that will affect your result, and it depends application to application whether it is giving positive impact on your application or not. So it will depend there.
Okay, ma'am. Ma'am, do we want to get the entire data set of I and V from the corresponding author for approximate the IV characteristics, or can we interpret the values from journals or surveys? Because I don't have the fabrication facility.
Okay, so what you are asking, I'm not getting your last question. Please
Ma'am,
repeat.
actually, can we interpret the values? The I usually in papers we'll be having R of R on R in it, and we'll be having I of I on values. So in fabrication related papers. So can we use that particular values in order to implement this
Yes.
function? We want the entire data set of V and I in order to approximate the complete graph of IV characteristics, ma'am.
Yes, yes. You can use that particular value, and in most of the paper, you may get the range, or they cited the paper from where they proposed that model. So in my case, let us suppose I'm following that Jacobic model. So you can refer that Jacobic model range also. If you are getting that model having range from 0 to 10, let us suppose, and that paper reported that they getting optimized value at 5, but you don't want to check whether it is giving best result at 3, 2, or 7 or 8. So you can check. But in my case, the reported value giving me optimized result. You can go for other values also. No need to stuck with those reported values only.
Okay, ma'am.
Yes.
Ma'am, actually for CNN, memories to base CNN, whether you're using MATLAB or Python, ma'am?
MATLAB.
MATLAB.
Currently MATLAb,
In
yes.
slide
You can use
51.
Python also, but I'm using MATLAB right now.
Okay, ma'am. Ma'am, in slide 51, ma'am, you have mapped the values to memristor crossbar structure.
Okay, this one. Yes.
Yes, ma'am. Ma'am, whether this is in situ training or ex situ training, ma'am?
Right now it's a access to training. We are just working over there.
Okay, ma'am.
Yes.
Fabricated a single device, and based upon the characteristics of single device, we have externally the trained in MATLAB, no, ma'am?
Yes.
So like that. Oh, okay, ma'am. Okay, ma'am. Thank you, ma'am. Thank you so much, ma'am.
Thank you.
Keitki Pathak, please ask your question.
Sir, may I?
Yes,
Because I have
yes.
already posted one question and one more query is there.
You can ask
This
your
thing
both
guys
questions
know.
directly.
Yeah. Ma'am, actually, I have been working for medical image compression on VLSI platform, in which I have used approximate computing. It is ADAS compression concept for image compression.
Your voice is
So,
not clear that much. Please speak louder if possible.
hello, is it audible? Hello.
Please speak louder. Yes, yes. Now it's audible. Please.
My question is, what if I am using, if I want to use approximate computing, like adder compressor concept or something like that, using memristor for just storage, because the concept of image compression is what we want to reduce the bits for storing purposes.
Yes.
So can we use for that approximate computing? Because when application is not asking for lossless compression, then approximate computing will
No,
do
then
the
you cannot go for
requirement.
approximate coefficient. If the application is lossless, then obviously in approximate you are compressing the image, so it's not a lossless. It's fully lossy system. So for lossless, you cannot go for this approximation part.
So where the modification we should consider only avoiding approximate coefficients only.
Yes. Means
Okay.
you cannot decompose that image if you try to go for lossless system. So you cannot go for this decomposition part.
Okay. And during your presentation, you have mentioned your result is always best suited for Haar basis.
Yes, yes. In my case.
There are other options like Debye, bi-orthogonal, all wavelets are there.
Yes.
I have worked in the dual tree discrete wavelet transform
Yes.
for the purpose. So, is there any specific wavelet decomposition method which will suffice the requirement of lossless or near lossless for memory requirement? Because Har is the very basic wavelet basis. So people are now going beyond those Har wavelet.
Yes, you can use, see, if you talk in terms of lossy systems, then I tell you about the Har, because I'm working with the lossy system. I want to save power consumption, I want to save area, I want to efficient storage of the device with the lesser logical operations. But if you talk in terms of lossless system, so better to go with TIFF type of image data and go for discrete cosine transform or Fourier transform, because there we having very less amount of loss compared to discrete wavelet transform.
Okay. And regarding your convolution neural network, you have talked about ResNet.
Yes, yes.
So there are also that is pre-trained network.
Yeah.
But suppose if we want to create our own model in CNN,
yes,
by increasing hidden layer or something like that.
yes, yes.
So if I am working in both platform like hardware and software result, so what would be the comparable parameter if I am going with the CNN network and some algorithm on hardware side? So which parameter I should, because sensitivity, specificity, all those parameters we can
Yes.
compute in a software basis. But when we want to compare the same concept on hardware as well as software, so at
In
that
what
time,
term you are telling that you are trying to implementing over the hardware?
suppose image compression.
Image
Okay, so in
compression, yes.
that is one of the application of image processing. So in that case, what happened, that compression ratio, PSNR, visual quality, all are there. If MATLAB or Python is there for just a compression purpose. Similarly, if I am considering my hardware platform at that time, storage and everything, that power, storage area that you are considering. So there is as such no match of the common thing between hardware and software.
Hardware
Purpose is same. Compression is same, but hardware and software are the different parameter that we are evaluating while doing image compression.
Do you talk in terms of memory strip model or some other hardware?
Memory stir.
Memory strip system. So obviously, in terms of memory strip system for crossbar array, if we are using for see in market till now, this memory strip crossbar is not that much globalized till now, but
yeah,
yes,
very
but
true.
yes, once it comes with its full specified material selections, because many more research is going on for improving its endurance, retention capacity, leakage current should be lesser and all. So once it gets specified with some specified material and all, so obviously it will give better result in the hardware form also.
Okay.
Is there any other
Thank
questions?
you. No, thank you, ma'am.
Is there any other question?
Any other question from participants?
Yes, Sumit. Actually, I have a still doubt on the one present slide. Actually, in the beginning of where the CMOS and memory devices are comparing. So
CMOS and memory device comparing. Okay.
yes.
This one, right?
No.
Then
I think where you the comparison between the CMOS and only memory having a table in the only 3 columns. I think I did.
this one is only that CMOS, memory and how
No,
much.
where you I think you have mentions the things like power required voltage for the getting the stored data from the memory store or CMOS. It's a slide. I think I missed the slide actually. Can you please up and down the
I
slides?
think this slide only I have where I compare this CMOS technology with the memory store.
Actually, one of the slide you have mentioned that. Yeah, slide number 3, right?
Right.
Yeah, slide number 3,
Yes.
I think.
This is slide number. This one.
Yeah. Yes.
Okay.
So basically, sorry, in the case of the transistor as well. So basically, in the case of the transistor, you have mentioned the required the source of the power source to retain the data. However, in case of the memory state devices, does not require the power source to retain the data. So basically, if you don't have any power source, how to retain the data from the memory state devices? Yes, I think I'm a little bit confused on that.
If you don't have power source,
Yes. So
you
how
can
to retain the data from the memory state devices?
see
How to read the data?
what the basic difference here. trying to mention that in case of transistor, you don't have any storage. Means once the power get off, so the electron charge get vanish from there. But in case of memory state device, even if power supply is cut off, so the past data, whatever, till the conductive filament is formed there, so till that
Sorry. I'm not going the switching mechanism behind the memory store devices. I'm just asking at a very fundamental things. So suppose that you don't have any power sources in the range of the milliampere or millivolt or microvolt range, and then you just need to know which bit are stored inside the memory store devices, like in 0 and 1. So how to know that? Because you don't have any power source to retain the data from the storage
you need to
device.
give very small amount of power for triggering that circuit.
Exactly. So I think the sentence are little bit misinterpreted on that table, I think.
Okay.
Yeah. Thanks for that.
Good observation. Thank you.
Okay. Is there any other question from participants? So if there are no further questions, let's thank our speaker. Thank you, Jyoti, for such an informative and wonderful talk. Thank you. So I request all the participants, shortly we will be sharing the feedback from for day 4. Please give your feedbacks by end of the day. It is very helpful for our future purposes. And please do join tomorrow at 9 a.m. For the last session. And also you can access the lectures of these video lectures on our YouTube link, which we have earlier shared with you. So thank you everyone. Today's sessions are over. Please do join tomorrow.